Hello, Saurabh. Hello, Saurabh.
Yes.
Yeah, am I audible?
Yes. We can start after few minutes. Okay.
Okay. Let's wait for 5 minutes.
Yes.
Hello, Saurabh.
Yes.
Yeah, am I audible?
Yes. We can start after few minutes.
Okay. Let's wait for 5 minutes.
Yes.
Hello, Saurabh.
Yes.
Yeah, am I audible?
Yes. We can start after few minutes.
Okay. Let's wait for 5 minutes.
Yes.
Hello, Saurabh.
Yes.
Yeah, am I audible? শুরুটা হও আমিও করবো ৩৩ জন অনলাইন আছে
We will start sharp at 1 o'clock. Arpan?
ওকে
হ্যাঁ, এবারে কাজ করুন। বলুন। তুমি আবার একটি ধরে নাও। No problem. I think we need to start, Arpon.
Okay.
Yeah. I hope everybody is ready.
Okay, good afternoon. I welcome you all the delegates and participants of this edition of IC2S, an international conference dedicated for interdisciplinary sciences. I am welcoming all of you on behalf of Dr. Orunima Bandyopadhyay. She is abroad and she is the convener of this event. Unfortunately, for time mismatch, she could not be live with us. and presenting her message as a convener. So I am taking the baton from her behalf. I am Arpan Bhattacharya. I am associated with Cynthia Scientific Research Foundation from its early days. And fortunately, our dream of creating a forum for interdisciplinary sciences is becoming kind of a reality, with this edition of international conference getting its due response from all the participants as well as the invited speakers and the delegates. I personally thank you all for your due diligence. So without further ado, I would like to start this session with our national anthem to be sung by Mr. Amog Varsha Arkini, a PhD student from IIT Madras, Department of Chemistry. I would request all of you to please stand up and start this session with our national anthem.
Thank you.
Thank you, Amog Varsha, for this wonderfully sung our national anthem.
Thank you, sir.
And now there is a video presentation from Dr. Arunima Bandhopadhyay. She has sent the video and Saurabh will play it, right?
Yes, yes. Wait.
Okay, let's start.
Hi, good morning all. Hi, this is Arunima and
My screen is visible?
Yes.
Yes.
So, are you getting her voice?
Yes.
Yes.
Okay, thanks.
hi, good morning all. Hi, this is Arunima and I'm very glad to welcome you all on behalf of Science Dialectica to the second of the series of International Conference on the Convergence of Interdisciplinary Sciences. So as the name suggests, we really see like merging of a lot of different disciplines here. Scientists and experts, professors from different areas of expertise are coming together for the next 2 days for a lot of very enriching and good talks. So it's a very exciting list of talks that we see up there, and the areas are also widely varied, from physics to AI and ML and waste management and nanosensors and whatnot. So really, it's going to be a really fun-filled next 2 days where we hope that we get a lot of learning, and we also get to connect with the people here. There are a lot of posters as well. So welcome on behalf of Science Dialectica. Welcome to the next 2 days of a lot of fun-filled learning. And again, I'm very glad to be part of this exciting session as well. Thank you.
Okay, I thank Professor Dr. Bandyopadhyay for her endearing speech and encouraging words. Now, the next session, it will be chaired by Dr. Sritoma Mukherjee, and she's a postdoctoral researcher in KTH Royal Institute of Technology, Sweden. And we'll start our sessions with her chairing over. Over to Sritoma.
Thank you, Arpan, and good afternoon, all of you who have joined in this session. And I am Sritama, and I thank Science Dialectica and SRF once again for giving me this opportunity to be present here. So we will start with the scientific talks, but before starting that, I would like to call upon our chairman and co-founder of Cynthia Research Foundation, Mr. Subhrangshu Bose. I would just briefly introduce him. He works specifically, his working area was mechanical engineering, automation, and process optimization. He is a key person of Kaizen business excellence model in manufacturing industries. And presently, he is working as Vice President of Ganges Manufacturing Company Private Limited. Previously, he has worked at several top management posts in different manufacturing industries. And he completed his postgraduate program in executive management from IIM Kolkata, and also postgraduate diploma in AI and ML from IIIT Bangalore. So I welcome Mr. Subhrangshu Bose for his speech.
I hope, actually, I am sharing his PPT on behalf of him. So his slide is visible, right?
Yes.
Okay. Welcome, Mr. Subhrangshu. Unmute, Subhrangshu, unmute your mic. Yeah, now I'm getting.
Yes,
Yes.
getting?
Yeah.
Actually, welcome all of present here. I am delighted and overwhelmed here. It is a great honor to address the second International Conference of Cynthia Research Foundation in front of highly talented scholars. On behalf of SRF, we want to give thanks to them who have been associating with us for 2 years or more, and specifically to whom those are tirelessly tried to build a small footstep of this organization without expecting anything. We are happy for getting a lot of participation at our seminar. This participation will give us strength and motivation, which will help to plan the next activity of Cynthia Research Foundation. When introductory parties here, whether a global pandemic, regional food shortage and famines, or escalating political conflicts and outright wars, the global problem of the present and future requires a rethinking of the way modern societies manage scarce resources, distribute wealth, and engage with each other. Solution to present and future challenges necessitate innovative and sustainable approaches, which will require investment in research, but more importantly, free places and spaces to think, develop, and innovate. Specifically, we are more focusing on the free places and spaces to think. Freedom to research is the key to ensure the future generation are able to exercise and enjoy the same, or at least similar opportunity that recent and present generation have enjoyed over the last decade. In other words, to ensure the coming generation are able to live in dignity and prosperity requires significant effort at multiple levels to ensure that current societies move towards a more sustainable way of living and exploitation of planet's resources. Our primary vision, what is our primary vision, basically? Right to get space for free thinking on science, one. Two, right to get opportunity of research for every common people. Three, build a self-reliant and sustainable economic model for a village through involving commons in research activity by exploring creativity of individuals. Specifically, this is our primary vision. Or broadly speaking, the primary vision of SRF is basically education movement, creating a model of one village-centered, self-reliant, self-powered research organization who fulfill primarily the bottleneck of that village, creating the skill upgradation opportunity and giving space for thinking with science and application of science to the children of that village. First we start with one village at 2023, next 2024 second village. That is our mainly target. And second, the target zone, which zone is mostly is targeted by SRF. We can classify our people in two domains, basically. One
extends its performance. Okay, and in terms of the bacterial reduction, so something around 6 log normal reduction of the bacteria concentration we have actually found out in case of activated carbon for different flow situations. Right. So for adsorption performance of activated carbon, we have used methylene blue as testing purpose, as because this is the common dye which we find out during flood coming from different textile industries mainly. And you can find out that very nice removal efficiency we obtain by this activated carbon, which is silver impregnated, something 95% adsorption efficiency we have found out, and removal can be done. This is for batch experiment, and for flow experiment also somewhere around 85% removal can be obtained. Okay, so I'll show you quickly that apart from the particulate film material as well as the the heavy metals and bacteria, we have to also take out the total dissolved solids. So for removing the TDS, we use the ion change resin. Okay, so these are actually poured in this kind of microchannel, and water will be going through this microchannel, and it will be actually reducing the TDS. We have started with TDS of 700, and this kind of channel can reduce it up to 130 or 140, which is the permissible limit for TDS. Okay, so I'll quickly show you that apart from that, at the last stage, we are also giving UV chamber. Through this UV, we are actually killing the bacteria and virus at the final stage. Okay, so this is the corresponding UV we have shown, having a battery pack over here, and both this UV and this battery is fitted at the bottom portion of the bottle cap at the end, so that the water which we are drinking, that is having no virus and bacteria at the end. Okay, so coming to the performance of this UV chamber, here we have shown that what is the transmissivity of the UV chamber in terms of fluence, okay, as well as how much it is its antibacterial capacity. So you can see from log normal 6 to more or less 0, it has been actually obtained, this kind of UV chamber whenever we are treating with flood samples. So these are some snapshots of the UV chamber exposure to the virus or bacteria colony, and you can see it is completely cleaning within 80 seconds. And we find out the retention time is little bit high. To have that high retention time, we are actually using the chamber thickness little bit higher. Okay, so that 80 seconds can be accommodated. Now, to improve the throughput, actually we are doing the parallelization of this unit. So you can find out that in a rectangular fashion, we are actually using 16 such channels, multiplex channels, and then at the bottom of that we are giving the this ion exchange resin activated carbon coated channels, as well as the your UV chamber also, to make it a compact design. Okay, so this is the compact form, whatever figure I have shown in the rightmost bottom corner. So this is having 32 individual units, and each individual channel unit is actually having 16 more channels, as I have shown in the previous design. So we have tested with the different samples, different flood samples collected from different rivers. Over here you can see starting from Ganga, Godavari, Krishna, and different flood samples also happening at Guwahati, Bombay, Hyderabad, Bangalore. And we have seen that very satisfactory performance it is giving. Approximately 40 to 46 liter can be filtered in 4 days. By the way, the movie of the filtration is being shown over here. And whenever we are going from parallelized module of 32 unit, so this is also giving 20 to 30 liter per 4 days. Now, to improve the throughput, what we have done, the design, whatever I have shown you, this kind of parallelized module, 16 of parallelized module, we have actually connected together in the form of a box, which I have shown you earlier. So I'll show you the final one. So this is the box, you can see the small one. Okay, this is good in submissibility. So as a result of this parallelization, we somewhere get 4.2 liter per hour, which is not a very low throughput. This is acceptable throughput in a flood-like situation, and it can work continuously for 6 days to generate somewhere around 600 liter, which will be serving a family for at least 10 days. Okay, so and the filtration efficiency continues to maintain somewhere around 99%. Okay, for up to 6 days operation we have found out. Okay, so these are the samples, whatever we have obtained before and after the filtration. So you can see outlets are always visibly clean, and this has been tested from in terms of TDS as well as the bacteria culture and the total dissolved solid, and you can find out outlet water is having proper drinking condition. You can drink also. Okay, and these are few data which I have quoted over here for your information, that before and after for 6 days of operation, what is the reduction of TDS, what is the filtration flux we get for different water, whatever we have actually tested. So with this information, I would like to stop over here. I hope I have not taken much time for delivering the talk. Thank you. If you have any question, I'll be happy to take.
Thank you, Professor Arup, for this fascinating talk, and it is especially more interesting to me because even I'm working in water treatment field, and seeing this prototype is very exciting, and to see that how a small cap in a bottle is able to do the magic and treat the water at the time of calamity. So I would like to ask if anybody has any questions from this talk.
Hi, I would like to know, I mean, you said that it maintains its efficiency for 6 days. So after 6 days, we have to change the whole module, or it can be repaired, or there are parts that can be changed which can again increase its efficiency.
So this unit, whatever we have prepared, some of the units, like that resin, we can actually recharge. Recharge means you have to do a reflux of the resin. So in the device only you can charge some chemicals. Okay, we do using this NaCl dose over there. Okay, and some units like activated carbon probably will be degrading, but it has been prepared in a modular fashion, and it is serviceable also. So you can take out that chamber and then put a new one. Okay, so but the price of these units are very low. Means the device whatever I have shown you, that will be at present I am having the cost of 500 rupees. So it's better to have another unit in place of doing the servicing. But in case the flood situation is not going down, and you have to reuse it probably with some common chemicals which are available around, like salt, etc. Charging will help you a little bit.
Oh, thank you.
Thank you. Any more questions? I have a small question. So in case of floods, you have shown that how you have optimized the pore wall, and you are removing most of the particles from going into the active channels for increasing the filtration efficiency. So my doubt is, like, in the flood situation, do we really have control over the size of the particles which is going into the bottle, and like how do we handle that scenario in case larger particle goes inside and it probably can clog because the unit is quite small. So how do you see that scenario?
Yeah, actually what happens, if you have seen the arrangement of this bottle is actually inverted fashion. So the larger particle will be settling down at the mouth of the bottle cap without even entering in that one. And for entry of water in the bottle cap, we give one U channel. So it's a straw which is fitted in the form of a U. Okay, so means if those are heavy particles, so definitely those will be actually going down. That will not be taking the complex path of U channel and enter into the filtration unit. Most of the cases, what happens, we find out while we have done the experiments, that just at the entry of this bottle cap, the heavy particles are being gathered as a mud. But anyhow, the performance of the filtration cap is not being hampered, as because the water entry is coming from little bit higher end with some U channel projected upward side. So if the dust particle loading is very high, so in that case you will be getting good amount of mud at the bottom mouth, but the filtered water still can be obtained.
Okay. Any questions from the audience side? Okay, if they're not, then I would like to thank Professor Arup Das again for this wonderful talk, and
Thank you.
we would like to move further on to our next speaker of this session. So our next speaker is Professor Arghanaran Banerjee. He is currently a professor in School of Mechanical and IT Engineering, Yungnam University in South Korea. He has completed his PhD from Jadavpur University and done his postdoc from US. And he has several awards to his list, and he serves as editor and guest associate editors and and member of editorial board in several reputed journals. And his research interests include nanostructured thin films, wide bandgap metal oxides, transparent nanoelectronics, supercapacitors and hydrogen storage, field emission devices for vacuum microelectronics, transparent thin film junctions for UV-based solar cells, carbon-based nanomaterials for sustainable development, and I guess much more. So, Professor Arghanaran Banerjee, welcome for your talk.
Thank you, Dr. Sultama Mukherjee, for the introduction. So first of all, I would like to thank SRF and SD team for inviting me in this conference, and especially thank to and congratulations to Shubhranshu for this excellent initiative, and it's really a great vision what I see from his presentation, and I would like to be involved in this initiative whatever capacity I can. So let me try to present my work. So my topic is importance of nanomaterials in Internet of Things. The focus will be on graphene. I will just go on a broad presentation, will not go to deep science, just broad broad things and what's going on in this field and the market's prospects. So first of all, what is Internet of Things? Now, Internet of Things, let me put a pointer here. Yeah. Now, Internet of Things, or IoT, is considered to be a network through which data can be transferred without having human to human or human to machine interactions. So it can be an interrelated system consisting of devices. Devices can be physical devices or mechanical, computational, or digital devices, or objects, animals, people, and these are categorized as things. And each of them are having some unique identifiers with the ability to transfer data over the entire network, which is the internet. So this is the connection between the internet and the things, and that's how this term IoT is coined. Now, what is the examples of this IoT? For example, a person with a heart monitor implant having an internet protocol address and is able to transfer data over the network. So for example, if suppose a person having a heart monitor implant and suppose he's having some malfunction in his heart activity, so those data can be collected and transferred to a suitable network, and through which the proper actions can be taken. So this is the basic of is a farm animal having a biochip transponder through which we can trace those animals, or an automobile with tire pressure monitoring built-in sensors, or a jet engine that is connected with a large number of sensors to collect, transmit data for its efficient operation. And also, it can be a smart cities filled with sensors to help understand and control the environment. Therefore, the basics of IoT is that almost every physical object can be converted into an IoT device via connecting to the internet that can communicate information. It is a sensor network of billions of smart devices that connect people, systems, and other applications to collect and share data. So basically, IoT is converging the digital and physical universes, and already various industries are already implementing IoT for efficient business. And another concept is coming out, which is called Internet of Everything, or IoE. And IoE is based on the model of all-round connectivity. It is based on 4 pillars, which is people, things, data, and process, where IoT deals only with the things. That means IoE is the broader version of IoT. The philosophy of IoE is to interconnect the whole world through trillions of sensors implanted into several billions of devices, objects, machines, to make them smarter. Now, IoE encompasses the connectivity between people to people, or people to machine, or machine to machine, thus encircling the people, process, and data. So this is the basic concept of IoE. Now, whether it is IoE or IoT, the market has a very high potential. Currently, almost all the market fields are already implementing IoT. For example, it is in education, transport, energy, grid, business, home, healthcare, any other industries. You can find IoT platforms, and currently almost 10 billion connected IoT devices are there, and it is expecting to grow almost 22 billion by 2025. And the market of IoT has already reached almost $520 billion US in 2022, and it is a growth of almost 50% in each successive year since 2017. And this IoT revolution is possible because of already we are having very low cost, low power sensor technology. Much greater connectivity is there. We are also having new concepts like machine learning, deep learning, artificial intelligence, big data, cloud, fog, edge computing, blockchain, etc. So all of these, when combined with IoT, it can implement Industry 4.0 on a wide scale. So therefore, the advantages of IoT lies in its ability to access information from anywhere, at any time, on any device, without human intervention. This leads to improved communication between connected electronic devices, thus saving time and money. So that is the reason IoT is now considered to be the future of the market strategy. Now, IoT features and technologies, especially IoT features, involve some identifiable or addressable objects. We need artificial intelligence to analyze those data. We already need very good connectivity. We need sensing, detecting, actuating systems, and most importantly, size should be small, because if we want to implement these sensing devices on billions of devices, therefore this sensing or detecting or actuating devices should be very small for efficient operation. And on the other hand, the IoT technologies involved RFID tagging, Wi-Fi, barcode, QR code, Zigbee, which is also a high-level communication protocol in a small personal area network. These are new concepts are coming, and obviously we need sensors and small. This is the way we can implement IoT through wearable sensors. We need motion sensors, we need piezo sensors, chemical sensors, some electronic tattoo sensors, etc. These are all should be used to implement it in the proper application in the IoT platform. Now, as I discussed in the previous slide, that size is very important, because to implement these sensor devices properly to collect data, size should be very small. Therefore, it should have higher efficiency. Therefore, there is a convergence between IoT and nanotechnology is coming, which is going to evolve a new concept called Internet of Nano Things. Now, before that, I'll just go briefly about nanotechnology, because most of you already know about nanotechnology or working on nanotechnology. So I'll just go very briefly. If there are some undergraduate students are there, for them I'll just explain very quickly what is nanotechnology. So it is basically a concept of manipulation of matter at atomic scale. It can be nanostructures, it can be nano devices or nanosystems, and the dimension of the atoms are in the nanometer range. So that's the reason the name nano came. And if you discuss about how small is nano, you can see that when you agglomerate several number of atoms, the dimension is still in the nanometer range. And if we take a comparative size, this is the Intel chip. The smallest Intel chip is almost 10 times smaller than a width of a human hair. And inside that Intel chip, there is a 10 nanometer wide carbon nanotube. We compare this with this size of this human hair, it is almost 10,000 times smaller than the carbon nanotube. So you can understand how small is nano. And obviously, why nano? Because it's obviously the properties at nanoscale is increasing, better in novel effects, mainly quantum mechanical effects. For example, if you break down a bulk material into nanoparticles, its surface area increases. It can give very high catalytic properties. Its antibacterial property can increase. Its hardness can increase. Electron band gap can increase, which can have efficient application in renewable energy. Its electrical property, magnetic property, thermal property, everything can be improved. And because of that reason, nanotechnology is now applicable in almost every field, from drug delivery to food to cosmetics, biotechnology, textile, energy storage, electronics, communication. In every field, you can see the application of nanotechnology. And one of them, and very popular one, is targeted drug delivery, where you coat some antibacterial or some drug on a nanoparticle inside, inject into our body. They then transfer those drugs to these cancer. So this is a very broad way of explaining this targeted drug delivery. Obviously, there are more science involved in it, but this is the basics of applications of nanotechnology in various fields. Next is Internet of Nano Things, or IoT or IoT. What is the basic features of this IoT? It starts with some devices or sensors which collect data. Then they transfer the data over a gateway, and those data are then collected by data ingestion system. Then they are processed and analyzed through artificial intelligence or analytics, and then smart decisions were taken for proper application. So this is the basic 6 steps of IoT or IoT protocol. Therefore, you can see that amongst these 6 steps, the most important one is the first one. Therefore, among these components, the sensors or sensor devices are most important due to the fact that the sensor data are considered to be the ultimate truth, because the subsequent actions, smart decisions, and intelligent applications are dependent on it. Therefore, to fabricate a nano device, we need to concentrate on the sensor. Now, basically, a nano device consists of 5 components. The first one is a control unit, which is a combination of processing and memory unit, which is like our central nervous system. Then there is a communication unit, which transmits data at nanoscale. Then a reproduction unit, which assembles or reassembles the components and reproduces the data or information. Then there is a power unit, which provides energy. And the last but not the least is the sensing unit, or sensors, actuators should serve as a link between the internal nano world of the nano device and the outside micro world. Therefore, in the IoT era, the implementation of trillions of nano devices or sensors into billions of physical objects will be required. And the average cost of these IoT sensors or sensor devices are ever decreasing. Currently, it is less than 50 cents due to the advent of various novel nanomaterials and innovative and cost-effective nanofabrication techniques. Now, if we now consider various applications of sensors in the nano field, we can see that for the last decade, the number of publication on the conventional sensors like camera, radar, or LiDAR-based systems are going down. On the other hand, the number of publication based on the nano or nano sensor, nano detectors, or the application of nano in IoT field is increasing rapidly. The number of publication over the last decade. There is a small dip. This is because of the pandemic, but otherwise there is increasing trend. So this corroborates the importance of nanomaterials in the field of IoT or IoT and in sensor technology. Now, if we consider various nanomaterials for sensor applications like silicon nanowires, gold nanoparticles, carbon nanotube, or graphene, we can see that the number of publication over the last decade for graphene or graphene as a sensor, graphene as a biosensor, gas sensor, piezo sensor, or hydrogen sensor, or graphene as a whole in the IoT field is almost exponentially increasing. So this is showing that graphene stands out as a rising star in the plethora of nanomaterials as sensor and IoT applications. So therefore, we will here concentrate mainly on graphene. Now, what is graphene? Many of you are already working on graphene. So basically, it is a 2D hexagonal network of sp2 bonded carbon. Just like 20th century is called the age of plastic, 21st century is the age of graphene. It is called the wonder material because of its many unique and fascinating properties. It's extraordinary mechanical strength, extraordinary electrical conductivity, exceptional nanostructure, high surface area, thermal conductivity, stretchability, biocompatibility, and easy and simple, cost-effective, and scalable fabrication process. And because of that, graphene is now applicable in almost every field, from communication to environment to construction, space technology, AI, composite, biotechnology, catalysis, energy, sensor, nanoelectronics, device, biomedical, automotive, etc. In every field, you can see the application of graphene. Now, in the for the graphene synthesis, it's generally most used one is the exfoliation. Other than that, there is some ion beam irradiation, sputter irradiation, epitaxy are there for fabrication of graphene, and also conversion of graphene from other carbon nanomaterials like fullerene, carbon nanotube, graphite. Especially from graphite, oxidation reduction method is widely used for the fabrication of graphite to graphene. So these are some of the basic methods of the graphene synthesis. And when I'm talking about graphene here, I'm not just talking about graphene, pristine graphene, but I'm talking about graphene, nanomaterials or graphene nanocomposite or graphene oxide, reduced graphene oxide, all are combined into this field. And also some other cousins of graphene like graphene, graphine, grapheme, or graphdyne, etc. These are all are considered to be in this field of graphene. So some of them are useful for some applications, some other can be used in other applications. So in the field of IoT, now graphene has been used mainly in sensing, memory unit, and communication unit. And mostly explored field is the graphene sensors and detectors, because the information generated and collected by these sensor detectors would lead to the final outcome of the entire network. Now, what is a sensor? A sensor is a device which is used to measure a physical quantity and give the output in an easy to read format. There are other terms also like transducers or actuators, which are similar to sensor but have a different definition or slightly different work. But the technology involved in sensors is based on the energy forms that are used or transduced during sensing, and these energy forms are associated with particular observable attributes. For example, here the form of energy can be magnetic, mechanical, electrical, thermal, biological, etc. And these are the attributes used for the sensing. Now, one of the mostly used graphene-based sensors in IoT platform is the electromechanical sensors. These are piezoresistive sensors where is a change in the resistivity of the material is used, or piezoelectric sensors, change in the material's electrical property, piezocapacitive sensor, optical pressure sensor, tribological sensor, or iontronic sensor. So for these, all of these electromechanical sensors, graphenes are used because of its extraordinary mechanical properties, high stiffness, and extremely low mass, which is useful for high efficient piezoresistive sensing. So these are some of the applications or some of the properties which is very useful for these electromechanical sensors. Now, especially for these electromechanical sensors, wearable paper-based graphene sensors in the IoT platforms are very useful, and already it has been used widely. One of them is the graphene oven fabric piezoresistive sensor. And these kind of sensors are used for pulse sensing, or it can be used for human gait or respiration rate detection, speech recognition, pulse signal detection, heart rate detection, or human gait or human movement detection. All of these can be used by these graphene, paper-based graphene sensors in IoT platform. Similarly, graphene-based paper sensors are also used from some other smart applications, especially for touchscreen application. This can be used as a nano generator for energy harvesting. Graphene fiber optic sensors are used for measurement microphones. Also, paper-based deformable radio frequency identifier system to monitor human pulse signal by attaching to the skin can be implemented in IoT platform through graphene sensors. So these are some of the applications of graphene-based paper sensors in IoT platform. Similarly, people are already using graphene-based chemical sensors. Chemical sensors can be ion sensors, humidity sensors, gas sensors, or biosensors. Especially graphene and its derivatives are already using for various gas sensing applications, especially for environmental protection. Toxic gas sensing is important for sustainable application in IoT networks for smart cities. So these are also some of the applications of graphene-based chemical sensors in IoT platform. Another very important application of graphene-based gas sensors is the personal health monitoring in IoT platform. Now, human breath contains vapor of various volatile organic and inorganic materials like isoprene, acetone, methanol, etc. And exhaled breath of most healthy human being contains a certain concentration of some of these gases. Any abnormal variation can lead to an early detection in lung-related abnormality and cancerous activity. So therefore, these kind of graphene-based gas sensors can be used for early detection of personal health monitoring in IoT platform. And there is some other application also. One of them is graphene biosensors in IoT platform, especially for smart hospitals. Now, graphene biosensors are blooming in the IoT-assisted healthcare fields. Emergency healthcare services can connect homes with smart hospitals through electronic health records and enable to monitor patients' symptoms in real time. So this is another very important applications of graphene-based biosensors in IoT platform. So these are some of the basic sciences. I'm not going into details. Some of these back-gated or top-gated FET biosensors and sensor mechanisms are there, but broadly, these are some of the very interesting applications of graphene-based sensors in IoT platform. And recently, because of the pandemic, already graphene-based biosensors for COVID management is already in the market. One of them is SARS-CoV-2 microbial sensor system through graphene via IoT platform or paper-based graphene electrochemical biosensor for COVID detection, SARS-CoV-2 rapid plex, 3D printed COVID-19 test chip, laser striped graphene biosensor for COVID-19 management. All these are already in the market, which are based on graphene sensing and actuating through IoT platform. And another one is graphene-based e-tattoo sensors. So we can create this e-tattoo with graphene and it can be attached to the skin. And through this skin, human pulse, human's body movement, eye movement, all these things can be detected very efficiently. So these are some of the very important applications of graphene-based sensors in IoT platform. Apart
Small
from
interruption. Actually, the talk exceeded more than half an hour, so it would be great if you could wrap it up sooner. Yeah.
Sure. So this is a final one. Actually, this is showing that the graphene-based memory devices, apart from the sensing devices, memory and communication both are very important. So graphene is also used as memory devices like shape memory or random access memory devices. And also graphene is also used for the nano communication, through which those data collected from these nano devices can be transmitted to the suitable system. So these are the applications of graphene in IoT platform. So therefore, in conclusion, I say that this IoT can transform the connectivity of the world and implement this so-called Industry 4.0 very efficiently. For that, we need to implement the sensor technology more efficiently. For that, graphene is very useful. And this is because the IoT global market is predicted to grow almost 1.8 trillion US dollar in 2028. On the other hand, global graphene market is also predicted to grow almost 2.86 billion by 2027. And graphene electronics are also predicted to grow almost 613 million US dollar by 2025. Therefore, the future of graphene assisted IoT has the potential to be limitless. Generation of huge volumes of actionable data from billions of devices to automate diverse business processes may open up an entirely new stream of revenue. So these are some of the reference, and thank you for your attention.
Thank you very much, Professor Raghav, for giving such a broad and wholesome overview of this very interesting and emerging material, and giving us the idea about the whole the technical aspect, the market aspect, and things. Thank you so much for that. So as you showed, like, there has been rapid publications on graphene and graphene based technology and devices and sensors and whatnot. So what is the scenario if we really see that how many graphene based technologies are actually translating into devices in the commercial market? What is your take on that?
Actually, graphene-based electronics are actually there in automotive. Also, the graphene is there, especially this battery technology, and in supercapacitor applications, graphene is now coming in a very big way. Okay. And there are already some of the graphene-based supercapacitors are already in the market. Mm-hmm. So these are some of the applications are there. And also in some of the other, like I would say some renewable energy field, like solar cells, or in other applications, graphene oxides are also very useful, because graphene is a zero band gap material, so it can be only used as a good transparent material and for a conducting purpose. But graphene oxide is having some band gap, and graphene nano ribbon, that is also creating some band gap. So because of that, this graphene and these derivatives, not just graphene, but graphene oxide, reduced graphene oxide, and the other cousins of graphene, especially graphene,
Yeah.
graphene, graphone, or just graphdyne, these are also come in a big way, and it's still in a nascent field. Although there are some in the market, but it's still not very strong market, but it has a very high potential. So
Yeah,
can be future, can
Yeah.
be the future.
for sure. We would like to take more questions from the audience.
Yeah, one question from audience. Can you
Sure.
turn on your mic? Yes.
Mr. Sunil. Please unmute yourself.
I can't hear.
Yeah, even I can't hear. I think he did not remove the mute of his mic. Any other question?
Hi. One question from my behalf. Actually, the sensors of nanomaterials itself, they are nanomaterials, but the whole sensor has not yet shrunk enough to be in the micro or nano regime yet. So IONT, so it's actually emerging field, right?
You're right, exactly.
When you mean IONT, then the whole sensor itself are embedded within that regime, right?
Exactly. That is what the concept is. It's still in the concept range, but that is what people are trying to make these nano devices, which will be in the nano range. The data collection, data transfer, communication, everything should be in the nano range. So we should have the nano sensors, then the communication should be in the nano scale or in the nano regime, and then the smart decision will be taken later, but this data collection and transfer should be in the nano regime. And this is a very important point, that why this is very important. Suppose we are having some nano device or nano sensors connected with our body for heart monitoring, and in the night, suppose there is somebody has some malfunction in the heart. So what will happen is that the body will detect, the sensors will detect this abnormality, and it will transfer those data quickly to some internet connectivity system, and it will go to the nearby medical center, and through AI, some smart decision will be taken, and promptly some action can be done. So this is the way so many lives can be saved, because we know that this heart malfunction in the night during sleeping, it occurs in a large way. So this is one of the applications of IONT or overall IoT in the health monitoring system. This is one of the future applications, but obviously it is emerging. So obviously we need to shrunk it down. So still open field.
Hello,
Thank
am I audible, sir? Yeah.
Yes.
Hello. Okay. So I want to ask about the things graphene. So graphene used as a filler material or other polymers can be used. So we can make a point of care testing device as a like graphene. We are trying, but some of the floating, like density of the graphene is like very high, so it is floating on that surface. So can we reduce the density using like mixing of graphite and other things?
Yes, that is very important, because there is several papers where there are applications where we need to take out graphene through floating process, but you are trying to do in the opposite way, right? We don't want it to float, right?
Yeah,
That's
graphene is going to float on that surface.
Yeah, that's true. That's true. So I think only way should be you need to make some composite. If you use pristine graphene, then it may be very difficult. So you need to create some graphene nanocomposite, and if you can create graphene nanocomposite with some transition metal oxide, or other things, because I don't know about your application, but depending on the application, if you create some nanocomposite, graphene and some transition metal oxide composite, or graphene polymer composite, similar kind of thing, through this I think you can improve its density without compromising its property. So you need to have a trade-off between the property and density, and then you need to choose your composite material properly. If you can do that, I think you can get some good data, but obviously you need to do some research, what kind of composite you want to, or what kind of material you want to combine with graphene. This depends on what applications you are going.
Yeah, actually, I am working on electrochemical sensors. So we are fabricating polymer composite electrode, and we are using that polymer composite electron measuring like diabetes and glucose.
Okay.
And
Okay.
so,
Okay. Yeah.
thank
Yeah,
you
so I
for
think graphene can be used, but you need to make some composite. Yeah, that should be the way to go.
thank you so much.
Yeah, sure.
Thank you. Any more questions from the audience? Okay, if there is no more, then thank you so much, Professor Argo, for such an interesting talk and a very nice discussion on the same. So we will proceed further to the next talk of the session. I would like to welcome Professor Abhishek Chaudhary. He is currently working as associate professor in IISER Mohali. And before joining IISER, he was postdoctoral research associate and academic visitors in several world-renowned universities. His research interest is to understand the physical properties and biological and physical properties of biological and soft condensed matter systems. Those are driven out of equilibrium. He uses both analytical approaches and computational methods to investigate the dynamics of the systems, ranging from the cell membrane and cell cytoskeleton to polymers and colloids in confinement. And the title of his talk today is going to be Chemotaxis and Collective Behavior in Active Matter. So we welcome Professor Abhishek for his talk.
Hi, I hope that everybody can hear me and
Yes.
The slides are also visible.
Yes.
Okay, thank you. Thanks a lot for the very kind introduction, and it's a pleasure to be part of this initiative and this conference that is going on. I mean, of course, there are quite a lot of old friends that I'm meeting here as well. Orgo being one who is, of course, my batchmate, and it's a nice, very nice talk, Orgo. And also a very nice conference organized, of course, by the enthusiasm of Shubhrangshu, who has been kind of on my ears for quite a long time now about this initiative, and the way that he is working is a real pleasure to see. And his vision, I hope that it takes shape as we go along. So today, of course, I mean, in the last part of the last conference that we had on this, I had broadly talked about active matter and given you a glimpse about what active matter is and how it works and all that. So today, the topic of my talk is again something to do with active matter, but more specifically about chemotaxis and collective behavior. Of course, the first question that we would like to ask is, what is chemotaxis? And the chemotaxis is the ability to navigate in chemical gradients, and it is crucial for the survival of microorganisms. It allows them to find food, so the microorganisms move towards the place where there is food, or even to escape from harmful toxins, because that is also something that is a behavior which is essential for them to survive. Now, what also happens is that several of these organisms can also produce the chemicals to which they respond themselves. Okay, and that's kind of something which we call as autochemotaxis, and this is used for signaling, and also forms a basic communication channel, which allows ensembles of microorganisms to coordinate their behavior. And examples of such situations are embryogenesis, formation of biofilms, cellular aggregation, and all that. Now, Obviously, as you can imagine, that this is not the only kind of taxis that is possible. Of course, microorganisms or organisms also show ataxis for various other gradients, such as if you have a temperature gradient or some light intensity. So that's one of the very interesting areas which has been emerging now a lot, where you focus a light and then if the cell or the organism behaves in a certain way. You could have a viscosity gradient, which is of course what happens when you are when a cell moves on a substrate, because that's how it has to sense the substrate, and depending upon the elasticity of the substrate, the cell will move in that direction or not. And this is very crucial inside, for our body and other aspects as well. Okay, so that's the broad idea about taxis, and also specifically about what chemotaxis is. Now, let us look at a few examples of what chemotaxis is. And the first example that we would like to look at is this example of what we all are very familiar with, is a bacteria called E. coli. Now, E. coli is a cell which is propelled by a rotation of helical flagellar filaments. And these filaments can arise at random points on the surface. So there are these filaments, there's a cell body, and there are these filaments which are on the surface of this E. coli cell. And what happens is that these filaments, which are long, but very, they are very small. I mean, the diameter is about 20 nanometers. Now, and they are also driven, these filaments are driven by a rotary motor. So what happens is that the cell would tend to move in a particular direction if these filaments form a bundle. Okay, and they will just form a bundle, or they would just stumble and move erratically if the bundles come apart. So let me just show you a movie of the same. So this is a movie which is taken from Howard Berg's lab, and this is a beautiful example of showing how this running motion is happening. As you can clearly see these filaments, and what happens is this running stops the moment these filaments are going to open up, and then they show a tumbling motion. Okay? So that's how this run and tumble motion happens. Of course, as you can imagine, this run and tumble motion happens. And specifically, if there is some gradient which you have, there's a food somewhere which the bacteria can sense, then this will move towards that direction. Or if there is a harmful toxin, it will move away from it. But it does so by doing this kind of sensing motion. As you can imagine, if it was moving in a particular direction, that would not be so efficient, because then it would have to constantly switch directions, and therefore the tumbling part of it is actually extremely crucial. Okay, I hope. I'm still audible, right?
Yeah.
Yes. You are.
Okay. Fine. So now, what you can do is try to find out what happens. You can, as I said, that it is not only about the single cell behavior, but you're also interested in looking at the collection of cells and see what happens. So the next one that the next example, the next part of this E. coli video, which I'm going to show you, is where they are taken in a agar-rich medium. I mean, there's some let's say a nutrient-rich medium, and what happens is in that nutrient-rich medium, these cells actually start elongating, and they will produce more flagella. And now, once they do that, then what happens is that they would move over the surface of this substrate that is there, and they will move in a coordinated manner. Okay, and this is how they do so, and you can see this beautiful behavior of what goes on as they are moving in a coordinated fashion. All these bacteria together are moving in a very coordinated fashion, and at the edge of the cell, at the edge of this swarm, so this is what this entire thing is, what I'm calling as a swarm, they form something called they form a monolayer. Okay, at the edge, you can, if you tag the cells and look at the velocities and all that stuff, you will see that these cells are stationary, and at the back there is the cells are quite active, and all that stuff. And you can see this brilliant kind of fluidic motion that is going around, and all that stuff. And you can, of course, there's a lot of study on this area. So this is one example. This is an example of an E. coli. You can also look at our favorite example of ants. Everybody has seen this example, of course, as all around us. And if you look at ants, this is an experiment where the pheromones that the ant releases is actually marked. So every time the ant is moving along this line, and every time you can see this red trails which are appearing. These trails are appearing because they are marking the pheromones. Every time there is a deposition of this pheromone, this is being marked and on that substrate, and so you can see this very nice trails which would be formed, and you can look at how this trail formation happens in ants. Okay. You can also take ants in a confined system, as in this other movie, and try to see, and these are fire ants, and these are you can see their collective behavior. Since there's a confinement, they will try to move towards these edges and then see how this behavior of these ants are, and they will at local places they will try to form these nests. And the question is that this collective behavior, can we extract what is what is being shown in this kind of biological phenomena to extract physical models which will help us to understand how this actually is taking place. Okay. These are, and you can see that this movie has the ants, and they formed a really thick trail along this direction. So these are the two examples that we have talked about. Now, slightly more on the second one that I showed. What we have done here is to this paper tried to explore is to understand social interactions which can lead to motility-induced phase separation. Now, motility-induced phase separation has been a very hot topic of research in the last few years, because of the fact that this is what active matter has been shown that there's a phase separation that can happen due to motility, and so this group tried to see whether this can be looked at in fire ants. See, these fire ants has a certain length, and there's they have taken in a circular cell. The cell height is slightly larger than the height of the ant, as you can imagine. So the ant doesn't move out of it, so they're in that confinement. They're confined in these 2 dimensions. Now, what you do is to view the entire thing from the above. What you look at is, first of all, the average speed of the ants as a function of their center to center distance. Okay, so it's like, so you fix some r equal to 0 or some reference, and then you look at how the speed of the ants from r equal to 0 onwards. And you see the behavior of that, and from that behavior, what you try to get is to some sort of an effective potential of interaction between these ants. Okay, some interaction potential which you try to extract from there. Okay, so if you then what the understanding is that if they are actually going to show us motility-induced phase separation, as has been observed in model systems where you write down in a computer program, then maybe these ants are going to show regions of heterogeneous. Heterogeneous like regions where they will cluster, and then the other places they are going to be like moving around. And within this cluster, you would expect that these particles should be stationary, and whether you can see that as you increase the density of this system. So as you increase the density, so this is when you look at let me just play both of the movies, and so you see that when you're looking at very high densities, you can see these regions which are forming. Okay, this is like these clusters of these ants which are absolutely stationary. The other places the ants are moving around, but if you look at let me just go back and play this movie once again. You can see that at these these are the regions where these ants almost come to a static. They are not really moving, but around them these are ants which are moving around. Okay? So these are so that's really kind of something which says that yes, indeed, in this case, you do see also a motility-induced phase separation, and there is a very nice theoretical understanding of this, and they have brought up. There's a lot of analysis which has been done in that paper, and so you're free to look at it. Of course, our interest, as I said, is also to look at what happens. If you have, please note that there are, if what I said in earlier, that taxis could be because of the overall gradient which is imposed, but could also be because of the fact that these individual elements are themselves secreting chemicals and are moving accordingly. Okay, so these are the two. So this will be differentiated between the taxis which is coming from an overall gradient to something which is like an autochemotaxis. So it's like doing it by its own. Okay, taxis which is brought about by its own. We could also, as I said, now therefore, if I look at what happens to a response of the system in presence of something like a gradient that you apply, and very interestingly, this is another again very recent and interesting paper where they looked at chemotaxis under flow disorder, which shapes basically microbial dispersion in a porous media. So what the device consists of is a disordered arrangement of discs and this crescent-shaped obstacles, which serves as an analogous of porous media. And you'd use a syringe pump to withdraw fluid at a constant flow rate. And then valves are used to initially fill the device with first a particular solution. And then what you do is to put another solution, okay, a second solution. You do it by using this syringe. So then you see how the this bacteria which is inside, there is a bacteria which is filled inside this in that region. This is the bacteria is a Bacillus subtilis bacteria, which are shown as blue dots in the images that you can see at on the side. So how does it respond to both a chemoattractant and a chemorepellent? Remember that we can have a chemoattractant which will be moving in the direction of the higher gradient of concentration, or chemorepellent, it will move out. If there is a region of where there's a lot of chemical, then it will tend to move away from it. So there can be two different kinds of such chemotaxis, chemorepellent or chemoattractant. And so you can look at what this behavior is, and you can see some very different beautiful behavior that you can observe. And this is, of course, again a movie which shows that how these these bacteria will as a chemo, depending upon whether there's a chemoattractant or a chemorepellent. So this is a chemorepellent, and because of the chemorepellent, you will see that these blue dots of this, which are this bacteria, actually move away from this fluid which is being injected. This is from this direction the fluid is being injected. I hope you can see my arrow, the arrow that I'm pointing on this screen, and the blue dots move towards the other side. Whereas in this case, where you have a chemoattractant as opposed to a chemorepellent, so this is a chemoattractant front. In the presence of the chemoattractant front, the bacteria show a very different behavior as we would have expected. There is also a very interesting behavior. These crescent-shaped things are actually quite important, because they wanted to probe also to the fact that whether they because these crescents actually are like regions where these bacteria can go and sit, even though there is a flow around which is dragging them out. Because these are regions of high concentration of this chemoattractant, and therefore they will go and stick there. And so you can look at all this various properties of how this system behaves. Okay, so this is one type of response in bacteria. You can look at a response in ants as well. Remember the ant system that I was showing you, and you can ask the question that if I now do a heat treatment, and see what the heat treatment is, whether if supposing there's a region where you have these ants and you have this they form nests at particular regions, so they are all they want to stay together at that place. They're there. This nest, now if I apply a temperature field, whether this nest is going to break up or they are going to stay, and you can see different kinds of behavior depending upon these two different heat treatments. So in this case, this is a higher heat. The temperature is higher than the temperature that is applied there, and you will see that the response of this ants, and how do they do that? In both cases, they would react to it, but in one case it would try to break up, but then again form back. Whereas in this case, it will just dissipate out, and it will just move out of this complete of this nest, and then do a different kinds of a motion. Here you see that it has already broken up, and it is going to move out of this nest because of the fact that it's feeling higher heat, and it wants to move out of it. And again, once it is doing that, it is moving in a very coordinated fashion. And the question is how it works out, because there's obviously an interaction between the ants which is telling them to move in that way that they are doing so. Okay, so that's about all the examples that we have talked about. Now the question is, how do we theoretically understand such systems? Because that is the kind of that will give us a lot of understanding about what are the predictive properties, and then maybe we will be able to devise better methods to understand these systems. The way to understand, for instance, if I'm looking at isotropic particles, if I take an isotropic overdamped Brownian particle, it's like, because of this is if you're don't worry about it too much. It's basically saying that this is the overdamped limit, so therefore you don't have an inertial term. All that you have is something which is like your drdt, which is like the velocity, and the velocity would be proportional. The velocity of these particles would be in the direction of the chemical gradient. This is given by this gradient of C with some beta d, which will tell you, this beta d, whether it is greater than 0 or less than 0, will fix you whether it's a chemoattractant or a chemorepellent. Now, this is the motion of the particle in the presence of this chemical gradient. But there is also a noise, overall noise in the system, which is thermal or in origin, and therefore this can be, there's a way of how to write down this noise statistically. What you can also do is, because of this fact that this particle, the motion of this particle in the presence of this chemical would be slaved with the chemical field, and so the chemical would also have to be, the dynamics of that chemical would also have to be written down. So you have to write down a time evolution of this chemical, and so what the chemical can do, the chemical can diffuse around, or it can, if there is a region, the particles, remember, we said that the particles can produce a chemical. So this is this second term that I have in this equation. This is the part which is, this is basically the del squared C, which is, if people will identify as a diffusion term. This is the part where at sources, at these places where these particles are, they are going to deposit some chemical, and that is given by this rate of chemical deposition. What can also happen is that depending upon how much chemical it is there and in that place, could be an evaporation of the chemical as well. So this is what the entire coupled system of the position and the concentration looks like. And you can solve this set of equations. What you will see is that depending upon whether the beta, as I told you, it's chemoattractive, this can lead to self-trapping of particles, which can either be permanent or transient. Permanent because if k is equal to, so this k naught, if the kd is equal to 0, obviously you will see that there at some places there is a buildup of chemical concentration, and the particles, if there is a chemoattractant, the particles will go and stick there, and they will, it will be basically self-trapped and will not be able to come out of it. But it can also do so by the fact that there is a noise which is there. It can come out if there is a sufficient noise in the system. In the opposite case of chemorepulsion, that should lead to self-avoidance. So they would not want to come in regions of this where these particles are, because they will lead to more deposition of these chemicals, which would therefore lead to particles avoiding to come to those regions. And so this is what it is. And therefore, you can do this system of two chemoreactive particles and show that it is like a very nice predator-prey system, which can model a predator-prey system and all that. However, you are also interested in not only particle behavior, but also collective behavior, because you now think of ensembles of these particles which are interacting via this self-producing chemical fields, and whether you can write down the corresponding equations in terms of the densities rather than in terms of the particle positions, but in terms of the densities. And yes, of course, again, you can do so. And again, you can write down very nice equations for the densities in terms of the densities, and try to solve for this. And this is basically this equation, this set of equations. It's called basically the Kähler-Segal equation. Some of you may have already identified what this equation is and what it does. It gives you a range of things. First of all, there is a uniform phase is a disordered one, and if you do linear stability to look at the stability of phases, you can show that there's a stability criterion which is called the Kähler-Segal instability, and depending upon that, you can have a particle aggregation if there is a chemoattractant. So beyond a particular depending upon a particular criterion, as I said, that this equation which is set about, I don't want to go into the details about, but it's fairly easy to find out what it is. So this scalar Segal instability can lead to formation of clusters and co-located chemical clusters, which can coarsen and coalesce and can lead to dense macro cluster at late times, which actually resembles something which is like a gravitational collapse. But again, so quite interesting behaviors you can see from the collective behaviors, which the model predicts exactly what is seen in the experiments. Okay, so it's very well characterized. What we wanted to wanted to look at was that so most of these kind of systems where the way they are defined is to see that the walker modifies the environment. Of course, I mean, think about the the particle as the particle's motion as the walker. So it's like a particle which is moving around. So that's the walker. So this walker can modify the environment because it obviously deposits chemicals in some place. Now, what happens is if you introduce a time delay kind of a situation, so it's like the influences them at some later time. So it does deposit at that place, but then it in turn influences them at a later time. Then what happens to this system? So we considered first a case of a single walker, which is performing a random walk in 2 dimensions on a certain lattice. And then so this is a paper which is recently come out. So we look at the dynamics of the walker is specified by some certain rules. So the walker generally would perform a biased random walk on a 2-dimensional lattice. So this is like if you think about it, it's like a diffusion of this particle on some substrate. But it now could move to a particular site because of the fact that there is a chemical present in that site, because the particle would try to move towards that direction. The chemical Q, of course, is being generated by the walker, which deposits at its current position and with some rate. But the chemical also also evaporates with some rate. So essentially, exactly what we have been talking about before. Further, what happens is that you cannot just keep on depositing chemical. I mean, you can keep depositing chemical at the site, and so the chemical at the site can keep on increasing and increasing and increasing. However, we'll say that there is a saturation which it can reach, because obviously beyond some point there is no the chemical bias, and then what I'm trying to say is that the probability of the walker to move into the site will keep on increasing because of the fact that there is a chemical deposition at that site, and it will lead to this self-trapping. But we wanted to say that there is a saturation which will also happen. Okay? So the chemical bias needs to saturate with increasing concentration. It cannot just keep on, the chemical bias cannot just, the particles would not want to keep on moving in that region. It would want to come out of that if there is a saturation of that concentration. So that's something that we had incorporated in the system. And then we looked at what the system does, and we find that this walker actually can lead to this, remember this form that we had talked about, that it can form this, just go and sit in that site and cannot move out of this region. So it is trapped here, but it can also come out and form these larger trails. So that if you look at the trajectory of the walker, then what it shows is that you can form these extended trails, but you also form this sort of globule state. And so the question is that what it does is it shows you a coil to a globule transition, which is something which is people working in polymer physics would know, and that is something which is shown in the trajectory of the walker as a function of the deposition rate. Obviously, at very low deposition rates, if the deposition of the chemical is very low, then the walk is going to move around all the place because of the fact that there is no way that it can get trapped. However, if you increase alpha, which is increase the deposition rate, you would expect that the walker should get trapped. If the walker should get trapped, then the trajectory would be confined and it should show a globule kind of a state. So it's like from a coil to a globule transition. But then what it's also interesting is the fact that it again starts to increase. And this is something like which we call as a re-entrant transition that we observe in our model, which appears because of the fact that there is a saturation of the concentration. And therefore, once the system gets saturated with the chemical, the walker can now move out of that region. Even though initially it was trapped, it can now move out of this region and can explore the entire space. And so this is something that we have. So we have, we plotted the entire phase diagram of the system depending upon how the alpha betas change. I'm almost through. You can also look at the mean square displacement of the walker, and again you see that at a fixed value of the decay rate, and it shows different kinds of behavior. Initially, for very low alpha, there's a diffusive behavior. as the alpha increases, the walks become subdiffusive, and it again, if it's increasing in alpha, again it becomes diffusive, which is exactly kind of mimics the coil globule transition that we observed here. Finally, just to leave you at the point that if you take several such walkers, this rule-based thing that we have set in, what can it lead to? And that's the beautiful thing that we have observed, is that it can lead to this beautiful kind of trails formations over this two-dimensional system. And it depends upon different parameters. You can have regions where they form these clusters. There are some regions where they will be completely almost homogeneous. So you can see this trail formation. You can also see this kind of clustering formation. You can also see this homogeneous environment. So you see the whole gamma of behavior that is observed in experiments. This is when you have chemoattractant. If you put a chemorepellent, then you see a very interesting behavior that chemorepellent could also lead to clustering. This is something that we are trying to pose. I mean, of course, we are at the point of writing this up, but there's some interesting behaviors that chemorepellent could also lead to clustering, because of the fact that it pushes the particles away. And if you have at a sufficient density of these particles, then you can have regions where they will basically, because of the push, they will come together, and this is what you can see. And anyway, so that's other behaviors that we can talk about. Finally, I would like to acknowledge the PhD student who has been doing this work, Shubhasree. She's currently in the 4th year of her PhD. She has been working on this, and she's done quite a significant amount of work, which is also the multi-walker system. This work has been also done in collaboration with my long-term collaborator and friend, Debashish, who is in IIT Bhubaneswar. And I would like to thank you for your attention, and I would be happy to take questions. Thank you.
Thank you, Professor Abhishek, for such a wonderful presentation, and it was so interesting to see these beautiful videos, and those videos on ants. So
Yeah.
are they reported, or they are
Yeah, they are
observation
reported
from your lab?
No, not mine. So unfortunately I'm a theoretician.
Okay.
And, so I mean, I wanted to give tell you about the different experiments that are going on. And of course, the nice part of it is there's so much of beautiful experiments which are happening that you can actually take data from there and try to see how your system, whether you are because obviously it's, we understand that it is experiments is what drives whatever goes on. So that's kind of the experiments which are happening at so I gave some references. If you look back at them, I'll just maybe go back at some of these references. So for instance, this paper is in Nature Physics in 2021. The reference is there. I would be happy to share other references as well. I mean, so this one is in Nature Communications again in 2022. So very recent and experiments. This is of course experiment of E. coli, which Professor Howard Berg was actually student of Nobel laureate Edward Purcell. Of course, I guess a lot of people would know Edward Purcell's this book on electricity and magnetism, but of course he was also a Nobel laureate, and his PhD student Howard Berg, of course, went into doing these kinds of beautiful experiments on E. coli bacteria. He also has a very beautiful book called Random Walks in Biology. It's actually a fascinating book, and I would urge any undergrad, grad student, and in fact anyone to go through it. And there's also some fascinating lectures which are there in YouTube also you'll find. So these are, I'll be happy to share links or whatever if anybody is interested.
That would be great. But one very laymanish question that I have is why people chose to read ants? Is there any reason behind it?
Absolutely. So no, that's fair enough. I mean, so see, first of all, is one thing is it's easy to see and easy to video them and look at their collective behavior. Ants, this is only one small subset of behaviors that they show. They do, some like mind-boggling things. You will find them forming bridges actually. So if there is if you look up for instance videos on YouTube as well, you'll see that how they form a bridge is also something worth looking at, because they they will build so few ants will step, and then the others are essentially like holding them. then few crawl on them, and then they come in the front, and then the few others crawl and then come in the front.
Wow.
So they actually form a bridge between, let's say,
Yeah.
if they have to cross a region. So
Yeah.
that's how they are going to do that. And
Yeah.
then they are going to, forward, they are going to move from one space to another. So this is one of the like fascinating
Yeah.
things. But there are, of course, so collective behavior became a big thing, of course, when people realized that, how do these different kinds of organisms, going from fish shoals to birds or ants, or if I go to even smaller scales in terms of molecular motors, or all this kind of stuff, they are obviously out of equilibrium systems. And in order to understand your equilibrium, statistical physics is no longer going to work, because your systems are naturally or inherently driven out of equilibrium, because of the fact that there's a definitive movement that do. I mean, we humans, crowd movement, like all of these things is very, very different, and it's not defined by equilibrium stat physics. So how do you build up how do you describe such systems? So if you have to describe such systems, you better understand them better. And so then obviously you have to do experiments to understand this kind of behaviors. Then people looked at cells and collections of cells, and looked at different kinds of things. But people have been looking at these experiments for a long time. But more attention has happened over the last decade. And now you have seen there's hundreds of new experiments every day which are coming up, and the behaviors that we've been looked at.
Amazing. In the slide, like which you talked about the chemoattractants at the end.
Yeah.
What was it based on? I mean, there also you have taken any organism?
So no. So basically, I mean, that's the thing about doing theory. Actually, you can you take an elephant and you think that it's like a
Yes.
particle. So you don't care about what is going. I mean, so obviously there is no. Of course, you can do some more serious stuff by trying to say that there's an asymmetry, shape asymmetry that you can build up by taking particles. Also, I mean, there's ways of doing it. But here in this case, our main intention is to first look at what can give rise to this kind of phenomena. And so therefore, the point is to have the same kind of physics which is being told us from the experiments, which is that the particles are going to deposit a chemical. So you have a chemical grid, if you can call it. And so these particles are moving on this chemical grid. And so if there is if it moves in a certain region in that chemical grid, it is going to deposit that chemical. And then obviously if there are other particles, and the other particles will tend to move in that region, because to that there's a certain bias. So it can move in all possible directions, but there is a overall bias in the direction of the chemical gradient, because it will want to move towards the direction of the chemical gradient. So if it does so, then it will just then it can move in that direction. And so then you evolve the system and see what this system is going to give you.
Sure.
And so and then you can because of the fact that you, as theoreticians, you can easily change the parameters. And then and so you change the parameters and see whether at different stages of these parameters you see these different kinds of behavior, whether you see this trail formation, to formation of these clusters and all that stuff. And there is a logical way of doing it, obviously, as to how you change the parameters, whether it makes sense that this is what it is going to predict as well. And you can then go back and say, okay, this is what we are getting, and so the prediction is that is probably what is happening in the system, and so this is what it can lead to. And come up with this kind of result. So that's
wonderful. I can go on and on, but
sure.
But we will look for any other questions from the audience because of the limited time.
Sure, absolutely.
Yeah. Any other questions, please?
Yes, I have a laymanish question actually.
Sure.
So the parameter beta, as you described, it takes care of the chemical to be attractive or repulsive, or the value the value signifies how much attractive it is or how much repulsive it is, right?
Yeah. So basically, exactly. So in the theoretical thing, yes, that's exactly what it does. So basically, you just keep on. I mean, it has to. I mean, so it's always good to make everything dimensionless, and so therefore there is this. But you can, in principle, you can give a unit what unit you are talking about in terms of alpha, what we call as. like we do in chemical reactions as well, right? When you do write down equations in chemical equations, then we will say the rate of something happening
Yes.
depending upon it's a first order or second order and all that. So similarly, you do it for alpha and beta as well.
So based on that, I wanted to ask that when the interaction is happening, I mean, when they are actually moving due to that chemical gradient,
Yes.
Is that interaction changing the very nature? If that interaction changes the very nature of the chemical itself, is it also taken care by the equation you have?
Very nice question. Yeah. So basically, so this is the thing. So you're right. I mean, so for instance, if the particle is moving and moves into a region of where there is a, so it's also depositing its chemical and therefore continuously changing its environment. I guess that's what you're saying.
Yes,
and yes, I mean, so obviously every time it changes its environment, that it wants to take the next step. In the next step it wants to take, it finds that it's a changed environment. So therefore the bias will therefore automatically depending upon how the environment is.
So if there is an inherent change in beta itself, I mean,
no. So the rates of the alpha and beta as the system progresses, the alpha and beta don't change.
Okay.
Yeah. Because then of course it is very difficult to monitor anything, and yeah, I mean, so yeah.
Okay.
Any other questions? I would be happy to say, or I mean, I guess I've already utilized more than what time I had. So, but yeah, anybody who wants to ask or want to ask me questions or anything like that, you're happy to contact me, and I would be happy to.
Sure.
Yeah. Thank you so much. Yeah. Okay, I guess I can.
Your microphone is mute.
Yeah.
Okay.
Sorry. So yeah, thank you so much, Professor Abhishek, for this beautiful presentation and a very nice talk, and it was very informative for layman people like me. So yeah. So as he said,
thank you so much. Yeah.
Yeah. As he said. If any more questions, people can directly contact him or write your curiosities and question in the comments. We can always address them later. So yeah, we will move forward.
I'll stop presenting then.
Yeah. We will move forward in our scientific talk session with the last talk that we have here. So the next speaker that we have is Dr. Kaushik Bagani. Senior researcher from University of Basel in Switzerland. He has his PhD from Saha Institute of Nuclear Physics in 2016 and was a PDF in Weizmann Institute of Science, Israel for quite some time. And his research interest consists of condensed matter physics, graphene, magnetism, superconductivity, squid microscopy. And today's talk that he will be is titled as Magnetic, Thermal, and Topographic Nanoimaging with Scanning Squid Microscopy. So I welcome Dr. Kaushik to give his talk.
Well, I don't know if you can see my screen, like the presentation.
Right now I can see a PDF of the schedule.
Okay. Let me stop sharing. I don't know what happens. Yeah, now a tab, a window. Yeah, now I can. Yes. So I hope you can see my screen now, like
not
the presentation.
Yet.
No,
not yet. Yeah, it's coming. Yeah. Oh, yet to go to the slideshow mode.
Okay.
Yeah. One last thing I will just add. We are probably running quite late in our schedule. So
okay, I'll try my best.
Yeah, please. Yeah, thank you.
Okay. So thank you for the nice introduction, and thank you for inviting me to share our recent work in this nice conference. So okay, as you have introduced me, I'm Kaushik Bagani, working at the University of Basel. And today I will be presenting our work, which is on magnetic and thermal imaging using a very novel technique, namely scanning squid microscopy, based on an atomic force AFM cantilever that we have developed in our lab recently. So this image that you are seeing on the screen is actually one of the very first images of a magnetic image showing the magnetic field lines of a bar magnet This image was actually made by Faraday back in mid-19th century using a very simple method with some iron fillings. But nowadays, these magnetic imaging techniques are way more advanced, giving invaluable insight into the magnetic texture, spin configuration, the domain formation, and even the current distribution in a quantum systems. And this kind of informations are invisible to the topographic or optical images. Neither it can be probed with bulk magnetization measurement or like heat capacity or the bulk electrical resistivity measurements. And this magnetism and the superconductivities are very sensitive to the local environment. And that's why this nanoscale magnetic imaging is required in order to understand these systems better. On the other hand, thermal imaging techniques actually provides us information about the energy dissipation, which is the fundamental process associated to the scattering, decoherence, or loss of quantum informations. And then nanoscale thermal imaging could provide us a new set of information which would be very helpful in order to understand these systems and in order to improve the device performance. So the scanning squid microscopy is a technique or a platform that can provide us both magnetic and thermal imaging with a single device. And today I'm going to show you a glimpse of this technique that we have developed in our lab. So this is the brief outline of my today's talk. So I'll briefly introduce you to the scanning squid microscopy. Then I'll show you our recent development in this technique based on a cantilever for a very robust scanning probe for magnetic, thermal, and topographic imaging. And then I'll show you an example of like prototype that can image the magnetic and thermal imaging with the same device. And then finally, I'll show you a very preliminary result on our recent experiment that we are doing on a two-dimensional magnet. Well, now let me start with the squid. Actually, what is a squid? Squid is a short form of a superconducting quantum interference device, which is schematically represented as a superconducting loop with two Josephson junctions, which is shown here by this cross. So commonly, these Josephson junctions are realized with a very thin barrier of a non-superconductor between two pieces of superconductors. And having these two Josephson junctions or barrier forms a squid, kind of like looks like this. This is the common squid that we have in our mind. But this can also be realized with a very narrow constriction of a superconductor. So like this narrow constriction of a superconductor between two pieces of superconductors, it can also form a squid. And today I'm going to show you the squid, which is this kind of weak link or constriction type superconducting junctions. Since this superconducting wave function has to be single valued going around this loop, this leads to a quantization. And as a result, the critical current that can pass through this loop or through the squid oscillates as a function of applied magnetic flux through the loop with a period of 1 flux quantum. The period of this oscillation is exactly 1 flux quantum. And since this flux quantum is a very small number, one can use this device as a very sensitive magnetometer. And in fact, this is this is the most sensitive device for measuring magnetic field. And a typical sensitivity is of the order of few microfarad per square root of hertz, meaning that you can measure this period of this field with a precision of 10 to the minus 6 of this flux quantum. So there are several different ways of scanning this device on a substrate and produce magnetic images. And one of the very first method is that people have used is making this device on a flat substrate on a silicon chip, and then scan this silicon chip on top of a surface of a sample and produce magnetic images. But this method has a drawback. Because of this very flat planar geometry, you cannot get very close proximity to the surface, so you lose magnetic sensitivity and spatial resolution. This issue was addressed by Professor Elie Zeldorf at Weizmann Institute by fabricating a squid, nanometer scale squid, on the apex of a very sharp tip. With this sharp tip, the squid is actually sitting at the very end of this apex of this sharp tip. And since this tip is very sharp, you can get very close proximity to the surface. And this is how the squid on a tip attains very excellent magnetic sensitivity, which is of the order of a few Bohr magnetron per square root of hertz. Meaning then this the squid on a tip has an excellent enough sensitivity to detect a spin of a single electron. Not only that, since the squid is sitting at the apex of this quartz tip, this is well isolated from the thermal bath. So it is also recently shown that it can also be used as a very sensitive thermometer. And it was demonstrated as a very one of the most sensitive device for thermal imaging at cryogenic temperature with a thermal sensitivity sub-microkelvin per square root of hertz, which is 4 orders of magnitude better than any other thermal imaging probes that are available. But however, this method also has a drawback as a scanning probe. You can go very close proximity to the surface with this sharp tip, but this kind of tip struggle to control the tip sample distance as it hover above the sample while imaging, and which increases the risk of crashing this tip onto the surface, and it makes our life challenging, like scanning very challenging. So this is not a very robust or very good way of making magnetic or thermal images. So in order to address this issue, we developed a new technique, squid on a cantilever. So our idea is to combine the scanning squid with atomic force microscopy. So I think we are more or less familiar about atomic force microscopy, which is well known for topographic imaging. In a typical atomic force microscopy has a cantilever, and the end of the cantilever we have a very sharp tip. And this cantilever is driven at its resonance frequency, and as the tip gets very close to the surface, the tip feels the van der Waals force, and the resonance frequency of the cantilever shifts. And by detecting this shift in resonance frequency, we can control the tip to sample distance. And since these cantilevers are very soft, it can detect this tip sample interaction from a large distance. So we actually wanted to utilize this property of the cantilever for good tip sample distance control. And for that, we have developed a method to fabricate a squid on the apex of a cantilever so that we can utilize this cantilever's tip sample distance control and scan with this squid, which is sitting at the apex of this cantilever. And this makes our scanning very robust. And now we have an excellent tip sample distance control from more than 1 micron away from the surface. And with this newly developed technique, we can do magnetic, thermal, and topographic imaging with this method. So now question is, how do we make such a squid on this apex of a tip of a cantilever? So we actually start with a commercial cantilever we buy from the companies, which is designed for like non-contact mode AFM techniques. Then we, with a focused ion beam, we mill away the sharp tip and create a small plateau in this area. And the typical size of this plateau is a few hundred nanometer, like 500 to 700 nanometer. And then we deposit a superconductor on top of this cantilever, on the front part of the cantilever. Then again, with the focused ion beam, we mill away the long trench along the cantilever up to this plateau. This is how it looks like. So we have a long trench along the cantilever, which creates 2 superconducting leads on the both sides of the cantilever. And on the apex, we create a squid structure by milling a small hole and creating 2 narrow constriction type Josephson junctions. So here is our 2 narrow constriction. We have a loop. We create a squid at the apex of this cantilever sitting here, which is connected to 2 superconducting leads, where we make our electrical contact for the further characterization. So this is the method of making such a squid on the apex of a tip of a cantilever. And using this method, we can make a squid with a diameter, effective diameter, few hundreds of nanometer, which is our spatial resolution of the magnetic or thermal images that we're going to produce. So now let me show you how do we measure magnetic field and temperature with such a squid. So we first cool down the squid at liquid helium temperature at 4 Kelvin, because otherwise the superconductor doesn't become superconducting. So we have to work at low temperature. And this is our measuring circuit. So we bias our squid. This is our squid here. We bias our squid with the voltage source here and measure the current through the squid. And here is our typical IV characteristics of squid measured at different applied magnetic field through the loop. So you can see as we increase the bias voltage, the current through the squid increases linearly up to a critical current, and then the characteristic changes. And you can see after the critical current, the current through the squid is strongly dependent with the magnetic field. Now here I'm showing the quantum interference pattern, which is basically this IV curves, like multitude of IV curves taken at different magnetic field and plotted in a different way. The color plot here is the differential resistance, which is to identify the superconducting state, which is actually calculated from these IV curves. And the x-axis is the magnetic field, and y-axis is the current through the squid. This blue part is basically superconducting part of our squid, and where we have this transition correspond to this transition here. And you can see the critical current nicely oscillate as a function of applied magnetic field through the loop. This is kind of typical the squid behavior, as you can say. Again, coming back to the IV curves, this region where our current through the squid is strongly dependent on the magnetic field, if we bias our squid at a constant voltage by measuring the current through the squid, we can determine the magnetic field. And this is how we actually measure the magnetic field with our squid. And to obtain the magnetic sensitivity, we actually measure the noise floor, like white noise floor, and then we compare it with the magnetic response, which is basically the change in current with the magnetic field. And I'm not going into the detail of this. So the bottom line is that the flux sensitivity or magnetic sensitivity that we have achieved is around 200 nanofinite per square root of hertz, which is very comparable to the squid, the sensitivity of a squid on tip that I have showed before, which has kind of few, it can sense like few electrons sensitivity. Anyway, so this is how we measure the magnetic field. And we also know that like this magnetic field, the critical current of a squid also depends on the temperature. So here is a set of IV curves measured at different temperatures shown here. You can see in this area, the current through the squid is also dependent on temperature. So if we bias at a constant voltage, and if we measure the current through the squid, we see this kind of monotonous decrease in current through the squid. And again, the slope here gives us the thermal response. And then again, by measuring the noise floor, we obtain the thermal sensitivity of our device, which is roughly 600 nanokelvin per square root of hertz. So meaning this we can measure the change in temperature in 600 nanokelvin or sub-microkelvin change in temperature at 4.2 Kelvin that we are doing the experiment. So this is indeed very sensitive. It is actually 4 order of magnitude better than any other thermal scanning probes. So now we have a very sensitive squid sitting at the apex of a cantilever. The next step is to test its robustness as a scanning probe. And for that, we have developed the scanning probe setup, which is a kind of atomic force microscope that we have in our mind, similar to the atomic force microscope. But this is designed for low temperature operation. So our cantilever comes from the side, and then we have a laser interferometer setup to detect the cantilever's resonance frequency. And as this cantilever approaches close to the sample, the resonance frequency of the cantilever shifts, and this we can detect. And here is the shift in resonance frequency at a tip sample plotted with the tip sample distance, that Z, which is shown here. You can see we can sense the tip sample interaction from more than 1 micron away from the surface, meaning we have a tip sample distance control from more than 1 micron away from the surface. So we can approach the sample quite a controllable way and with a very robust way. So now using this thing, this squid on cantilever, we can now go for the actual real imaging. So we use normal standard non-contact mode AFM with our cantilever, and this is the sample that we have imaged for the first time. These are the array of permalloy magnets, and this is the atomic force microscopy images that we have done with our squid on cantilever. Nicely shows the topography of the sample, and since these are nanometer scale magnet, that creates the magnetic field, stray field pattern, which looks like this, that we have imaged with our squids. Now, if you're a bit confused how this kind of repetitive field pattern is created by these magnets, you can always overlay the topography on top of the measured images, and then you can easily identify the orientation of this magnet that created this field pattern. And this is one other advantages of having a topographic images alongside with your magnetic or thermal images that we're going to study. that we can always do one-to-one correlation, and that will help us to understand the sample better. So not only the magnetic imaging that I said, we can also do magnetic and thermal images. So in order to demonstrate that, we first image a standard sample, which is a gold thin film, which is made in this kind of serpentine shape. And this is the AFM image, which kind of mimics the shape of the sample, which is not very good because this is one of our very first images that we have taken from a large distance. That's why we do not have better resolution for that. But that doesn't matter with our magnetic or thermal images. So for magnetic and thermal imaging, we applied a current through this gold wire. And this current will create a biosabot magnetic field around it. And this field we can detect with our squid. And this is the Z component of the field, the biosabot magnetic field that this current has created, which we have imaged with our squid, which nicely shows the shape of the geometry of the sample. And not only the magnetic images, because of this current, the energy is dissipated and it increases the local temperature. And that temperature we can sense with our squid while we scan over the sample. And this is the thermal image that has been imaged with our squid, which nicely shows the shape of the sample of our gold nanowire. So now we can do the magnetic and thermal imaging simultaneously with our squid, and everything is set. Now actually we plan to do some actual imaging, study some material, which is currently that we are imaging a material which is two-dimensional magnet, which is chromium germanium telluride. So let me first briefly introduce you about the magnetism in two-dimensional systems. So there was actually a very long-standing debate about the magnetism in two dimension. Since the Manman-Wagner's theorem says that there will be no long-range magnetic ordering in a two-dimensional system at finite temperature due to the thermal fluctuation. But this thermal fluctuation can be counteracted by introduction of some kind of magnetic anisotropy. And recently, this has been proven to be true. In 2017, there was two reports on claiming the magnetism in bilayer chromium germanium telluride and monolayer chromium triiodide at finite temperature. And this discovery actually led the research in this direction of magnetism in van der Waals materials. One of the reasons is that this gives us a platform to study the magnetism in lower dimension. And not only that, there is a potential application of this material in spin turning devices, because with this van der Waals material, you can easily make several heterostructure with other van der Waals semiconducting materials. Not only that, this magnetism of this material can be controlled electrically by doping or gating, which is ideal for this kind of device application. So this actually motivates us to study this material with our squid on cantilever that can be easily probe the number of layers and how the magnetism behaves with our squid. And the material that we are currently studying is chromium germanium telluride, which is shown to be ferromagnetic down to 2-layer limit, with the Curie temperature is around 30 Kelvin. And this is kind of Heisenberg type ferromagnet with the magnetic z-axis is along out of plane direction. But interestingly, this magnetic z-axis can be tuned to in-plane direction with the application of electrostatic doping. And it was theoretically shown that this can be achieved by both electron and hole doping. And this actually motivates us to study this material. So actually how this magnetization evolves with the number of thicknesses and how it evolves with the doping. But unfortunately, most of this material, like 2D material, 2D magnetic materials, are doped with ionic gating, which is basically they put a blob of ionic gel on top of the material and then apply voltage to it to create high voltage for the doping. And this is not suitable for our scanning experiment. So that's why we took a different approach. So to dope the material, we chose ruthenium chloride, which is a crystalline acceptor, meaning it has a deep work function. It takes the electron from the material. So that's why we make a sample like this. We create a multi-layer structure with the chromium germanium telluride with ruthenium chloride. And then we encapsulate everything with the hexagonal boron nitride to prevent it from the oxidation from the air, so that we can study the material with pristine and also with the doping. So this is the sample how it looks like. This orange region is the ruthenium chloride, and this black dashed region is the chromium germanium telluride, or CGT in short. So first we image this area where we have mostly with the ruthenium chloride, meaning doped area. Only this corner is not doped. So first we take the images, like this is the optical image, and then we do our squid on cantilever. We do this atomic force microscopy, which nicely shows this the topography of the sample. And then for magnetic imaging, we first applied out of plane magnetic field to saturate all the spins along one direction. And then this is the magnetic stray field pattern that has been created by this magnet. And we have imaged with our squid. And these lines that you are seeing here is this basically the different step edges of different layers. And then by considering like we can also calculate the magnetization from this magnetic stray field that we measured with our squid, and this magnetization shows uniformly magnetized in different layers. And now actually we can calculate how many number of layers are there, but if we consider like theoretical value of this of the magnetization per chromium atom is 3 Bohr magnetron, and if we consider that, we identify the number of layers that has been contributed to the field that we have measured there. So this number of layers varied from 5 to 6 layer, 5 to 14 layers or 15 layers or something like that. That nicely matches with the thickness of the material that we have identified with our AFM measurement. Now to understand these magnetic phases better, we start sweeping the magnetic field. We started sweeping the field along out of plane direction. We started with the field polarized state, like saturating the field along one direction. And then as we decrease the field, initially nothing happens. Then when it becomes close to the zero magnetic field, we see domain is forming in the thinner part of the sample mostly. Then when we switch the field to the other direction, we see domain is formed all over the sample. Only this corner, the bottom corner of the sample, which is not with the ruthenium chloride, that didn't form the domain. But as we increase the field further, we see the domain is formed everywhere of the sample, and then it slowly saturates to the other direction. The key observation from this hysteresis thing is that the formation of domain at different magnetic field, and also the formation of domain at relatively higher field in the undoped region. So this could be due to the fact that it has a different doping concentration in different area due to the ruthenium chloride. So in order to confirm that, we image another area of the sample where in this bottom part of the sample is the pristine sample where there is no doping, and the top corner of the sample is with ruthenium chloride, meaning we have doping. So in this time, we instead of sweeping the out of plane field, we sweep the in plane field. So the hope is that if this doped region has different anisotropy, like in plane anisotropy, we should see an effect along the edge of the sample. So we started by polarizing the spin along one direction, that by applying out of plane field, and then we decrease the field almost to the zero. And this is the image at zero in plane magnetic field. We don't see any features in the sample other than this edge here, but there is no the line or no features along the edge of this ruthenium chloride. But as we start increasing the in-plane field at higher magnetic field, you see a line is forming along the edge of the ruthenium chloride. And at 300 millitesla in-plane field, you see a clear line along the edge of the ruthenium chloride. This may be due to this could be an indication that this part, the top part with the ruthenium chloride, it has a different anisotropy. But this is not clear yet. So we are still studying this material in order to understand what is the actual behavior of this material. So this is just a preliminary result. Okay, so with this, I would like to conclude that we have developed a new novel technique, squid on a cantilever, for a very hybrid scanning imaging technique. And then we have shown that this is a very robust and controllable approach, and we can do both magnetic and topographic imaging. Not only that, we can do the magnetic and thermal imaging, and you can image the current through a sample. And we are actually currently studying a material. We're trying to understand the role of doping in a two-dimensional magnetic material. So with this, I'd like to thank our University of Basel team, like Professor Martin Bozo and our PhD students and all our group members who are kind of involved with us for this project. And finally, I'd like to thank you for your kind attention.
Thank you, Dr. Kaushik, for a very interesting presentation on a very emerging field of that of cantilever merged with squid and giving rise to a whole imaging on a different level of magnetic and thermal way. So I would like to see if any people from the audience have questions. Yes, please.
Hi. Yeah.
Professor Abhishek. Yep.
Yeah. So sorry, Kaushik. I mean, I wanted to ask one simple question about this. This 2D magnetism that you are showing.
Yes.
Now, in two-dimensional materials, I know that this Marvin-Wagner that you mentioned. So the question here is that these layers are not it's not strictly 2D, right? I mean, so there is some it's quasi 2D type of systems. These are right. And the question here is that can we see at what point the Marvin-Wagner actually sets in, that you will not see a long-range order.
So these are actually the material that I showed. Actually, these are like quasi 2D, you can say, because this is multi-layer. But it actually has been shown in monolayers. The material that we have studied, I mean, now I do not have the data, but we have seen in 2 layers and 1 layer, which is there is a magnetism present. Like not only this material, there is a other material like ruthenium, chromium triiodide or chloride. They are monolayer material that shows magnetism. But this Marvin-Wagner's theorem only does not count. Sorry.
No, so please go ahead.
The Marvin-Wagner's actually doesn't count any the anisotropy. That's for any isotropic system, Marvin-Wagner's theorem. But if you consider any kind of anisotropy, then this theory doesn't valid. So then you can expect.
It's not valid.
Then you can expect some kind of ordering at finite temperature, depending on the anisotropy. Yes.
Right.
So there is no contradiction with actually there is no contradiction with the Marvin-Wagner.
That's what I was trying to understand. Okay. Thanks.
Thank you. Any other question? Okay, if there is no more questions, then I would like to thank Dr. Kaushik.
Thank you.
Arpan, do you have any question?
Yeah, a small question. Kaushik, is this whole setup made within your lab?
Yes, we made up everything from scratch. Yes. So from the cantilever to the scanning probe, yes, everything in the labs.
Okay.
Yeah.
So, I mean, it's a, tabletop system that you use every day like that?
No, it's not a tabletop system because we have to work at low temperature. So basically, the whole setup is basically there is a liquid helium dewar, and we have a like probe outside. We have inside this probe we have the setup like the scanning setup. Then we dip everything inside this liquid, and this whole like dewar is floating on a like isolation table. And so you can see if you see the image of this okay, it's not clear.
So you are using liquid helium directly within the chamber and putting the
no,
scanner
there is a vacuum
inside
chamber. No, there is a vacuum chamber, and the liquid helium is outside this chamber. Like if you have a normal transport setup, let's say, you have everything inside, then you close this thing, then you pump out all the air or whatever the thing, and then you
some
dip
kind of
everything
closed
inside
finger system is actually attached, which is cooling down the actual region.
There is a cold finger, yes, which is in contact with the liquid helium.
Okay.
That basically cools down our like scanning setup.
Okay. Okay.
Yeah, it's not like a flow chamber or something like that, because with the cantilever we need a vacuum kind of. We do not need high vacuum like ultra high vacuum chamber, but OK's vacuum is necessary.
Okay.
So we cannot do inside the liquid this
So
experiment.
you have tried on different magnonic crystal systems, scanning, and maybe different kind of thermal or microwave excitations to see what kind of spin orientation they are going into after equilibrium.
So not so far. I mean, we have been developing these techniques for like last almost 1.5 years, and then we have started with this 2D magnet, which is kind of now exciting field. I didn't look into these magnetic systems and all the spin wave systems, and it will also be a bit difficult to probe the spin waves or magnons in the system, because those are in atomic levels, right? So, and we have spatial resolution of 100 nanometer, 50 to 100 nanometer, which is we cannot probe.
Spatial resolution is the problem, right? Because you said that, I mean, the tip has the potential of actually picking up the magnetic signal from a single electron.
Yes, single electron, it can sense. Okay, if you have a spin of single electron sitting, if nothing is around, it can detect that spin. But if something is around with this like a spin wave, slowly the spin is rotating. So then it's basically, as a collectively, the total field is zero, like average out everything. So then we cannot see this oscillation on the spin wave or the magnons.
Okay.
So that's the limitation. It has a sensitivity if you have a like defect. If let's say you have a graphene sample, there is a defect, only one defect at the middle of your sample, then it can detect those. Yeah. But if you have like multiple of those defects around and that collectively gives you, if average out to zero, then we cannot see.
Okay.
Yeah.
Okay. Thank you. Fantastic talk.
Thank you. If there is no more questions, then I would like to thank Dr. Kaushik for a very intriguing and a very interesting talk.
Thank you.
And yeah, and with this talk, we conclude the scientific talk session. And I am so glad and happy to say that this scientific talk session can present a very nice example of interdisciplinary discussions where people are genuinely coming from various different fields and coming up with their expertise, and they are talking about so many different and relevant topics. So I would very briefly sum up what we really heard in this session. So we started with Professor Arup Das, who talked about the bottle cap design of a prototype to treat the flood water samples. And he talked about the numerical analysis as well as the experimental data that they got from the filtration efficiency. He talked about the passport optimizations, and he shared many results about the disinfection by the antibacterial material and UV and adsorption by activated carbon and so on. It followed by Professor Argha's talk on IoT, and his focus was on graphene. So he talked about the basics of Internet of Things, IoT, and Internet of Everything, that is IoE, and also the new concept of IONT, that was Internet of Nano Things. He talked about their market and their application in nano device, and he came on to graphene, its synthesis, and wide range of applications in sensors and IoT. The third talk was given by Professor Abhishek, who talked about the basics of chemotaxis. Beautiful motion videos were presented of bacteria and ants to study their behavior and motility, reaction to their boundaries and thermal gradient, followed by theoretical models and an analysis of active random walk. The last talk that we had was by Dr. Kaushik, who talked about the scanning squid microscopy, the basics of squid, the fabrication of squid on liver, how AFM and squid merges to utilize cantilever for fantastic magnetic and thermal imaging. So with this, we conclude the scientific session. Thank you all for being there, and of course it would have been even more better with an active audience participation, which we hope to get in the following sessions. After this, I would like to present our industrial sponsor of this conference, Bhomik Calculator, and we have Vivek Bhomik, who is co-founder of this company, Bhomik Calculator. And Bhomik Calculator is a manufacturing company. They manufacture mostly jute industrial machinery. And I would now ask Saurabh to present the video from the Bhomik Calculators, our sponsor. Saurabh.
Are you getting?
The video is not playing. I'm seeing myself.
Okay, just do it.
I can see a raised hand from Abhishek Chaudhary.
Bhomik Calculator jute division.
Are you getting right now?
Yes, it has started.
In
Yes.
the year 1978. We are manufacturing different kind of jute mill machineries. We manufacture carding machine, finisher carding machine, drying machine, and different type of spinning machines. We also manufacture calendar machine and twisting machine also. We have a fully equipped workshop with state-of-art facilities. All kind of modern VMC and CNC machines are with us. The company constantly works to develop its product to ensure high-class performance and productivity of their machinery. Recent past, we also manufacture AD, Afron Wrapped Spinning Frame, first time in India, to produce fine count of jute yarn. The company constantly working with government bodies like IJIRA and JTRL to develop and working different kind of innovative and development works. All the mills, all the jute mills in West Bengal, India, and in Bangladesh, almost every company are using our machineries. Our office, corporate office, is at Bowbajar, Kolkata, and our works at Shodhpur and Maniktala, Kolkata. We really feel privileged to be a part of this wonderful platform. Thank you.
That's all.
Thank you, Saurabh, for the video from Bhomik Calculator. Now, I would like to present IGUS International, which is the collaborator of Cynthia Research Foundation. IGUS International mainly works on smart polymer for robotics, and we have Mr. Nitin Prakash and Ragesh Kumar with us, and I can introduce. To introduce Ragesh Kumar, he is a mechanical engineer, and he joined IGUS in 2008. and he is working in low-cost automation department. He had opportunity to meet and support customers with IGUS products. We would be glad to have a few words from Ragesh and Nitin from IGUS International.
Thank you. Thanks, Sritama. Thanks for your introduction. And myself, Nitin Prakash Vibhandik, and I am also a mechanical engineer, and I have been working with IGUS since last 15 years. I have also completed a postgraduate diploma in business management, and I take care of the polymer bearings division of IGUS India. I'm a product manager. So I will very quickly take you through a few of our recent developments that we have been doing. I'm not sure whether my screen is shared. Is it?
Now?
Yes, we can see.
Okay, just a second. Can you see the presentation in the presentation mode?
Not now.
No?
We were seeing it in the beginning.
Okay, I'm sorry.
Can you share it again?
I'm sorry, I don't have an experience of working with Meet. We generally always use Teams, but I will try it once again. Just give me a second, please.
Yeah.
Is it visible now?
Yeah, it's loading now. Yeah, now it's visible.
Yes. Okay. So I hope now the screen is visible.
You can go to the slideshow mode if possible.
I'm in a slideshow mode already. Maybe it will take some. I think there is some delay. Maybe.
Okay. Anyway, it is visible. Yeah. Please go on.
Yeah. Okay. I'm in slideshow mode at the moment. In case it's not redirecting to the slideshow mode in the next 1 minute, please let me know. I will try once again. So welcome everyone. Today, I'm going to give you a brief introduction about the 3D printing processes that we are doing at IGUS for the VR resistant parts, and then Ragesh will cover for the low-cost automation related topic. So very briefly, IGUS is a company from Germany. Its headquarters is in Cologne, and the headquarters in India is in Bangalore. So there is a lot of information which is put up here in the slide, but I would not really take you through that information at this point of time because we are already running quite late. Talking about what exactly IGUS does. So we are into tribopolymers. Our specialty is developing tribologically enhanced engineering plastic compounds, and these compounds are used for sliding motions. Our mission is improve whatever moves without a drop of lubrication. So that is what we always strive for. And while doing this, we always think of making it carbon neutral footprint. So I don't really want to talk a little bit more on this topic, but I will directly take you to what exactly our compounding is. So our compounds are basically the engineering plastics with fibers and solid lubricants, and all this together makes our tribopolymers. Currently, we have more than 50 tribological polymers from IGUS. These are all homogeneous structures. They don't have any layers. It is having the same tribological property all over the wall thickness of the part. And all these bearings have been tested in our lab in Cologne in Germany. And as we have more than 6,000 customers in India and more than 20,000 customers all over the world, these products have been all the time getting tested with our customers. The advantages that IGUS products basically offer are they are self-lubricating, do not need any lubrication because they already have the lubricant inside, corrosion-free, lightweight, resistant to chemical and water, and have a very high wear resistance, which means a longer service life. We also have online life calculator for all our products, which means you can go to IGUS website, fill in your details of the application, what is the load, what is the speed, shaft material, all those things, and the calculator will predict what life you can get using iGUS products. As I mentioned already in my last slide, we have more than 50 standard plastic compounds, and these compounds are being used to make plain bearings, as you see here on the left corner, self-aligning spherical bearings, and also ball bearings. So what we have recently started doing is we also make materials for 3D printing processes, and we also supply, or we also support for the 3D printed parts itself. So we do parts as well as we do material for 3D printing services. Basically, we have three different technologies, or there are three different technologies which we follow. The first one is SLS, which is selective laser sintering.
The slide is not changing. I think
Sorry?
We are seeing only the first one. The slide is not changing. It is from the number one. Yeah, now we can see the 3D printing.
Okay. Shall I stop sharing and start again?
Yeah.
One second. I hope it's visible.
Yes, now it is
presenting mode. Yes.
Don't share your PPT. You share your screen. That will be good actually.
Yeah, that's what I was sharing my PPT, but just now I stopped it and started sharing my whole screen.
That will be good.
So now it's working, right?
Yeah.
Okay, so what you see here on the left hand side are the plain bearings, which are made from these polymers. What you see here are the self-aligning spherical bearings, and here are the polymer ball bearings. And then 3D printing technologies, we follow three different technologies at the moment: selective laser sintering, then FDM, which is fused deposition modeling, and DLP, which is the digital light processing. So I have a video here. I will quickly play the video, which basically explains how the selective laser sintering at iGUS works. Currently, iGUS is having 5 SLS powder materials in our range, which could be for bearing applications. So here is the video. Are you able to hear the sound as well?
So sir, volume is not coming.
Can you confirm, Shirish, if the voice is there?
No, voice is not there.
No? Okay. So I will just explain. So what happens in SLS printing is there is a layer of powder, and a particular shape is melted by the laser, and then the layer goes down by 1 mm, and then the next layer is melted. So layer by layer, the part is formed. What you see here now is the parts have been already melted, and the person in the video is now removing the parts which are made, 3D printed parts from the powder, and then these parts will be cleaned in the blasting machine, so that whatever powder is stuck onto the part could be removed. And this is how the parts are printed, 3D printed parts from laser sintering. So basically it works with this type of powders. And the blue color one, for example, which you see here, is an FDA compliant powder for food industry, and this one is specially for gears, and then there are 3 more materials which are suitable for self-lubricating bearings. Yeah, and then this is the FTM, which is fused deposition modeling. I think this is the very common method. Most of you are already aware, maybe. And for this, what we do is we provide filaments like this in a range of 10 different material compounds. And there is also a possibility of doing multi-material printing, which is generally not possible with SLS. As you see here, there are already 2 materials. The black color material inside is for the strength, and the white color material from the outside is for the gear profile. So this is done by FDM. IGUS provides filaments as well as service to support you with 3D printed parts by this process. So what you need to do is just go to IGUS website and upload your 3D CAD, and you will automatically see the prices directly on the website. This is a very new one. It has been started maybe 8 months ago in IGUS. It comes in the form of, the material comes in the form of a liquid bottle of 1 liter and half liter, and it is the digital light processing technology in which there is a bath of resin, what you see here, gray color. There is a tank or sink of resin, and again similarly as in SLS, here the liquid is pasteurized layer by layer using the UV light, and it needs again a particular kind of cleaning. Now for example, what you see here, the parts are being put into the chemical, and after that it will go into the ultrasonic cleaning so that whatever extra resin is there will be removed. And it also needs to be, I think, okay. Yeah, so these are the cleaned bearings, and these will be now removed from the platform. The advantage of this technology is it can produce very minute parts with very high accuracy. For example, very small gears like 1 mm, 2 mm are also possible with this DLP technology. Generally, SLS or FDM could not do such type of parts. Yeah, so that was very brief introduction of 3D printed parts from IGUS. There is a lot more to show, but I think today is not the opportunity, and the time will not be able to permit us to go far. So thank you very much for your time, and now I will hand it over to my colleague Ragesh, who will talk about low cost automation topic. And after his session, if you have any questions about 3D printing or low cost automation, both of us could be able to answer you together. Thank you.
Thank you, Nitin.
Yeah, Ragesh.
Please give me a feedback. I hope you can see my screen.
Yes, Rajesh, we can see your screen. Yes.
Yeah.
Just a small this thing that the below that button, that tab you can hide. Yeah, that's what.
Yeah. Thank you, Nitin. Thank you everyone once again, and giving us the opportunity to present IGUS product line. Now, as Nitin told about the 3D printing line, we also have other product line. It's called low cost automation. It is product from IGUS. I mean, we have different product lines, and we combine everything, and we offer a complete solution to customers. Not really complete solution, but I would say about 60 or 70% of the product or robots that customer gets from IGUS. Wherein you can see the three models, three different types that we have. First one is a Cartesian robot. The second one is Delta robot, and Robolink. We also heard about Abhishek sir doing research on the ant. I mean, I'm really not sure about the research what he's doing, but these robots could be helpful for for doing researches. I have some presentation in the upcoming slides. I'll show it to you. And also, I would like to point out the Kaushik's mention about magnetism and its research. So these products could be helpful for such research and development activities. And as I mentioned, these are the three robots that we have. These are the technical specification. Since we have a time limitation, I'm not going in depth. we can share you the information later with Madam. And you can now. What I wanted to add here is that we also developed the controller. So you get 3 robots and you can use the controller. In case if you have your own if you have your own controller, we can support with the drive systems. Then you can use your own controller. So I guess provides 3 robots: Cartesian, Delta, and Roboli, plus the controller. And these are the technical specifications. I will share you the presentation later. So as I mentioned earlier, we have we have this product line and we are combining everything and we are offering a complete solution to the customers or different industries, I would say. Now we have also the additions in the robotics section. As you can see on the right side, this is called the Rebel. This is very special for research and development activities because this robot, unlike other manufacturers, we use polymer gears inside the robot. So what you're seeing is a 6-axis robot, wherein we also have 4 axes. I have a short video to show you.
Yes, that is fine.
So I would like to also point out here the controller is inside this small base. So this is the robot, and it weighs only 8.2 kg. We can literally take it in our hand, and we can put it on any surface, and we can do the activities. And this is how the software look like. And this is very intuitive software for the users. So you can see the video. So it's connected to the. It can be connected to the laptop, and you can basically do the program. Yeah, now you're set.
Rajesh sir, we can share the video links to others. For this, we can summarize all. Yeah. In setup box,
Yes, we can
share the video links so everyone can see.
Yeah, we can see that. And so this is the Rebel, and what you are seeing on the right side is the Scara. Yes, we will share you the video, and this also could be very interesting for research and development activities. Now, what we are demonstrating is for component pick and place application, but we are already in discussion with different companies, especially doing lab, the medical research applications. So this video, because we have time limitation, we will share the video link later. I will go to the different applications or the simulations that we are doing in IGUS India. As the previous speakers were talking about their researches, so these components, these robots would help you to do the research. Now, this one is for the screen validation application. So you see the gantry robot, wherein they have fixed the stylus. The touching to touch the screen. They have used this pen, and they are testing the screen before it goes to their customers, their clients. And this one is for now everyone is talking about the electric vehicles. So this is for testing the car's parking sensor, testing the performance of the car parking sensor. So we have offered them a special gantry systems wherein they keep the sensor at the end and they do the research or they do the testing using IGUS gantry system. And again, this is related to the electrical control unit. So the customer wanted to test it with different angles. So we made the system really compact within 200 millimeters, and they do the research with this unit called Apiro Systems from IGUS. And this is a PCB board, as you know, and they do inspect using the IGUS gantry system. This is a short video of that. So they fix a camera here and they take a picture of it, then they analyze that. So these are the research, research applications that we are already doing it in Bangalore. Yeah, so that was about it. And as I mentioned, these are the customers already using IGUS robots. IIT Madras using it for. I'm not sure about the application because we have NDA filed, and this is from IIT Hyderabad is already using our two robots for their research, and this is a university from southern India, South India, and they have used our Delta robot for student training applications. And what are the benefits that you get from IGUS robots is that it is completely maintenance free, lubrication free, faster return of investment, ready to use, lightweight, and so on. So that's all. But I have a short video to share. I would like to also show you the demonstration of the robot. That's why I'm in office. So in 2 minutes, I mean in 1 minute, I think I will show you the robot. And you can please give me feedback if you're able to. I'll just bring the camera. Like this. As I mentioned,
Rajesh sir, it is not visible.
Can you please unmute your phone
Yeah,
mic?
it is unmuted. But I'm not sure how to turn the.
Yes, Rajesh, we can
camera.
see you now. We can see you from your phone.
Okay. Can you see the?
Yes,
Can you
yes,
see
we
me?
are seeing the Delta robot.
Yeah.
Yes.
So this is what you're saying is the Delta robot, and it is completely lubrication free, maintenance free. There are two variants available. This is smaller one. This is what we installed at Karunya University in Coimbatore, Tamil Nadu, and this one is the bigger Delta robot. But the interesting thing would be for you is this RoboLink. Actually, this is a 4-axis one, and as I mentioned earlier, all the links has polymer gears, so it is lightweight, lubrication free, maintenance free. Very special for research and development activities. And this is the smaller robot. We call this as a RoboLink DCI. In fact, we started developing this, and we made this system. Now we have introduced the robot called Rebel, wherein we have 4 and 6 axis. And the last one is the gantry. So we were doing hard disk screwing application yesterday, so we just kept the demo kit like that. So, and this stroke length can be customized. So that's all from me. Thank you so much. If you have any doubts, please.
Thank you. Thank you, Nitin and Rajesh, for sharing your activities at IGUS with us. Do you have anything more to say?
Thanks for giving us the opportunity to present here, and a special thanks to Subhranshu sir who gave us the chance. So it's really good to be a part of this event. Thank you very much.
Thank you again. Thank you. So I would like to call upon all the members in the audience who have joined us in this conference. This is going to be a photo session, the next 2 minutes. Please switch on your camera of your mobile or laptop, whichever thing you are using to log into our online session. Please switch on your camera so that we can take a screenshot. Others,
Please do fast.
yeah, please be little quick.
Can I take smile, please? One more. That's it. Done.
Is it done?
Yes.
Okay. Thank you, Saurabh, for the photo. Hope
I
everybody.
must say thank you to you. You seriously, you just amazing. You coordinated the session very nicely. So let's congratulate Sritoma to organize this session very nicely. Thank you. Thank you.
Thank you. Thank you, sir.
So I
Thanks,
think,
sir.
Sritoma, Sritoma,
Shitoma is frozen with happiness.
no, I think our network has issue. Sritoma? Okay, she will be joining in 1 minute. She has some issue with the laptop.
Okay, you declare the break, na?
Okay. So on the next session will be just within 2 minutes we will start. So next session will be chaired by Professor Arghunarayan Banerjee. So we'll back in 2 minutes only, just 2 minutes. Okay. Just stay tuned. Thank you. I think Sagar is ready. So I think we need to start. Professor Banerjee, you can start the session. I sent you a message. You just check it.
Okay. I have seen that one. Yeah. So, okay, then welcome to the second session of this international conference on convergence of interdisciplinary science. So, it's good evening from Korea, but still good afternoon from India. So, there will be, I think, 5 presentation. The first one is Dr. Sagar Ganguly. He has done his PhD in 2019 from IISER Kolkata. He is currently a postdoctoral fellow in the Uppsala University, Sweden, and his current research activities include materials chemistry and electrochemistry for energy applications. So his title of the talk, I again repeat, Nano Impact Single Entity Measurement Enables Plasmon Enhanced Electrocatalysis. Over to Dr. Ganguly.
Thank you. Can you see my screen and hear me?
I can hear you, but not the screen. Yeah, it is. Yeah, it's coming. Perfect.
Okay. Thank you for the nice introduction. And it's a pleasure to present my research on nano impact single entity measurements that enables direct plasmon-enhanced electrocatalysis. So when noble metal nanoparticles such as gold, silver, these are exposed to electromagnetic radiation such as light, the free electrons on their surface starts to collectively oscillate, and this is known as plasmonic excitation, which rapidly decays through Landau damping and produces highly energetic electrons and holes inside the systems, which undergoes carrier relaxation within picosecond timescale and produces hot electrons and hot holes inside the systems, which ultimately recombines and releases this energy as heat in the surrounding medium. Now, there has been an increasing interest to harvest these hot electrons and hot holes for catalysis or electrocatalysis. There is another viewpoint where the heat that gets generated from their recombination is also used as a source to enhance the kinetics. So it's kind of a thermal catalysis. So when we look at the entire literature, all the electrochemical studies has been done with ensemble measurements. Like you have a lot of nanoparticles, gold or silver, which you drop cast on conductive support, such as carbon or ITO, and then you do the measurements. And your activity actually depends on the arrangement of the particles, the thickness of the layer, the aggregation, and the collective heating. So in principle, you are first of all getting an average response. And second, we are actually probing the catalyst electrode assembly and not the true catalytic activity of individual nanoparticles. So here I propose a different technique of measurement, which is called nano impact single entity measurement. In this measurement, a very dilute solution of the catalyst is used as the electrolyte, and the ultra micro electrode having dimensions less than 10 micron is used, which is catalytically inert. When the measurements is performed, a nanoparticle from this dilute solution comes and collides with the electrode, then this surface becomes catalytically active and you see a current. And when it leaves, then again the surface becomes catalytically inactive and the current drops. So this is how nano impact single entity measurements work. And it, due to its randomized orientation of contact, no aggregation, it kind of addresses all the issues that one faces with ensemble measurements, and one can actually get the true catalytic activity of a catalyst at single particle or single entity resolution. So our motivation of this study was to evaluate the performance of single plasmonic particles in electrocatalysis. But before we started our measurements, we first checked the ensemble activity of the system. We chose glucose electrooxidation as the model reaction. And this is how the ensemble measurements were performed, where gold nanoparticles were drop casted on pyrolytic graphite electrode, and the measurements were performed with and without laser irradiation. So as we see, this is the LSV under dark corresponding to glucose electrooxidation. When the measurements were performed at 532 nanometer irradiation, which corresponds to gold plasmonic excitation, we see that there is almost a 40% enhancement in the activity. We then repeated the measurements. We did a chronoamperimeter measurement with alternating illumination, that is, we turned on and turned off light at a certain time. Now, just think about the system that these plasmon or the hot electrons and holes, they are very, very short-lived. So one would expect that the moment one will turn off light, they will be kind of instantly gone from the system. And so if these hot holes or electrons, they are directly responsible for the catalysis, there should be a sharp drop in activity. But what we observed is when we turned off light, instead of a sharp decrease in activity, there is a very gradual decrease lasting over several seconds. So this kind of tells us that no, the hot electrons or holes are not directly participating. It is somehow coming from temperature. And this response is actually limited only by the cell constant, but anyway. When we repeated the measurement, it's 650 nanometer where the gold plasmons are not active. We again saw that the enhancement, the behavior, everything is almost like same. So this first gave us the clue that at least for this kind of ensemble measurement, which has been routinely used so far, gold is probably not the primary absorber, something else is absorbing. So we checked the absorption properties of the entire electrode assembly, and we found that it is the pyrolytic graphite which has been so far routinely used as a catalyst support. That is the primary absorber in this case, and as it has almost uniform absorption across the visible region, so this pyrolytic graphite absorbs most of the light, leads to a temperature increase, which finally catalyzes the reaction. To confirm, we then repeated the measurements. We broadcasted the same amount of gold nanoparticles on top of ITO electrode, and this is how the enhancement looks like. But this also tells us another thing, that when these gold nanoparticles are in direct contact with the conductive substrate, be it pyrolytic graphite or ITO, the entire contribution from plasmonics somehow vanishes. We just do not see it. It's almost negligible. Now we come to the single entity measurements, where we first did some control experiments, where we just dispersed the gold nanoparticles. There is no glucose here. And we saw that this is how the baseline looks like in a chronoamperometry. So there are no spikes that you would expect for collisions. Then we just did the control without any gold nanoparticle with only glucose. The responses are almost similar. Now, when we do the measurements under dark, we start seeing spikes coming out corresponding to nano impacts of these gold nanoparticles on top of the microelectrode and then glucose electrocatalysis. We repeated the measurements with a 532 nanometer irradiation, and there is a significant enhancement in the peak current or the spike currents. Then with 650 nanometer, there is a this response is almost identical with what you see under dark. Then we analyzed the result, and we figured out that under dark and under light, the average charge per spike is almost identical, and they are actually statistically almost the same. But when we irradiate with 532 nanometer, where the gold plasmons are active, we see that there is almost a 40% enhancement in the average charge per spike. Now one can think from the previous bulk measurements that maybe the carbon microfiber that is used for making the microelectrodes, they are responsible. They are responsible for this kind of behavior. So we checked their absorption, and we saw that they have almost identical absorption here as well at the two wavelengths. So this is definitely not responsible for what we are observing, and it is the gold nanoparticles now which is the primary absorber and showing its response in the catalysis. So this table here summarizes the results so far. So when we are using this, which has been routinely used, the enhancement is identical at two wavelengths, and this is the primary absorber, not gold nanoparticles, which has been reported so far. And in these two cases, where gold nanoparticle is the primary absorber, when it is in direct contact, we see almost identical enhancement, no effect of plasmons. But in single entity only, it kind of enables the participation of this plasmonic effect in glucose electro oxidation. Now the question is why? To understand, we first have to see how direct contact disables the plasmonic effects. So this is how all previous reports have so far understood this system. So you have the particles on top of your electrode, you shine light, you generate electron and holes. The electron goes to the electrode, the holes participate in the reaction. But this is how we understand the system. Due to its metallic nature, the Fermi level of the gold nanoparticles is coupled with the working electrode potential. So when you are actually changing the potential at the working electrode, the Fermi level of the gold nanoparticles moves in tandem. So the moment you produce electron and holes on top of this system, these are actually potential perturbations which the potentiostat will try to quench. So the electron will be taken by the electrode. Electrons from the electrode will quench the holes, and you cannot see the reaction because this is generally much, much faster. But then why in single entity we actually see it? To understand, we just have to think of charge transfer and its distance dependency. When the gold nanoparticles are quite far from the microelectrode, there is no charge transfer that is possible. When it is at a distance which is approximately or less than 15 angstroms, now charge transfer can happen by tunneling through the electrolyte layer. And when this actually collides exactly on top of the electrode, there is definitely unhindered charge transfer. Now, when the gold nanoparticles are quite far from the electrode, you shine light, generate electron and holes. These cannot transfer or interact with the electrode, so they primarily recombine, and you do not see any reaction. The chronoamphogram is almost flat. In the second case, when it is inside, it is at a distance where charge tunneling can actually take place, you create the electron and holes. Due to potential difference, this electron will go to the electrode, but electrons from the electrode cannot quench these holes. So you can now start seeing reactions happening. And you see these kind of spikes. And when it is on top of the electrode, it takes some time for the Fermi level to equilibrate, and maybe by that time, the particle already starts to leave. And here also, the electrons can go to the electrode, and the holes which still is not quenched by the electrons from the electrode can participate in some amount of reaction. And you start seeing this kind of spikes. So, and there is one more way. So this is one of the way why we understand the hot carrier injection, where that's why this nano impact enables the plasmonic response. The other is thermal effects, because here when a particle comes to and does the collision, even before that it can get exposed to the laser irradiation, and as a result, it is already hot when it is striking the electrode. And this hotness or the enhanced temperature can actually catalyze the reaction, and that can be observed in the higher spikes. So in conclusion, we have shown that whenever there is a direct contact between the electrode and the nanoparticle, there is a continuous Fermi level equilibration, and one cannot see any contribution from plasmon due to the rapid quenching of the hot carriers by potentiostat. But in nano impact single entity measurements, there is a decoupled Fermi level that will allow for selective hot carrier transfer, and that will enable one to actually observe the plasmonic effects in catalysis. So with this, I thank my supervisor, Professor Alina Sekretareva Chow, who is a PhD student in our group, our division, and I also thank the funding agencies for funding this research and my stay at the university. And these are the references of the work. This is already published, and this we have archived recently. Thank you. I will be happy to take any questions.
Thank you, Dr. Ganguly, for this intriguing, informative presentation. So now the floor is open for discussion. So there is one question somebody is asking. You can ask questions, anybody.
Am I audible? Hello.
Yes.
Yeah, hi.
It's a nice presentation and basic of the plasmonics. So I want to ask a little bit about absorbance and oxidation of glucose. So does oxidation depends on absorbance?
Absorbance of what?
Absorbance of like whatever material you are putting on that HOPG or graphitic layers, like gold has absorbed, that material has absorbed that gold particles, and something oxidation in that electrolyte oxidation and reduction potential will be happen. That is depends on absorbance or not, that you have find by that like absorbance of that 230 nanometer something you have shown. My question is simple. Absorbance is depends on oxidation and reduction potential or not?
I'm very sorry, I'm not.
Actually, probably he's talking about that when your light irradiation is going on, you are observing the absorbance, right?
Yeah.
Yes.
So that absorbance is changing with the oxidation reduction potential of the electrolyte you are using, or
no. So if you use it depends. Like if you are using first of all, okay. So if they are drop casted on top of electrode, their absorbance is almost identical with what you'd expect. Like if you remove the contribution from the support and you just check the absorbance profile of gold, they're almost identical with what you buy from Sigma. But if it is in the electrolyte, there is a very slight, like 2-3 nanometer shift to the lower wavelengths. But I don't think it has to do anything with the potentials. Like I am really not able to connect how this can be connected, like absorbance with the
oxidation and reduction.
Because these are nanoparticles which and this absorbance is actually coming from the collective oscillation of electrons at the surface of the nanoparticles, and that is what is like the plasmonic excitation is. And it as far as I know, has nothing to do with the oxidation or reduction of these things, like the nanoparticles.
Okay, sometimes it happens in that electrolytes, because in electrolyte, whatever species we are taking, like dopamine and glucose in that electrolyte, so it's happens like oxidation, reduction, and that product and some reaction. That's why I asked. But agree that in case of plasmonics, maybe it will not happen. Thank you.
Thank you.
Any other question? So I have a question that you were telling that when the nanoparticle is less than 15 angstrom, so there is a charge transfer is going on, and before more than that, there is no charge transfer. So how you come out this number?
Okay. So this is like in principle. So if you check the literature, like what is the distance from which tunneling of charge can actually happen? So because here when it is like if the thing is, because if you look at the equation, the as you increase the distance, the amount of tunneling will go down almost exponential, because you have like e to the power minus beta d. So you increase the distance, and so like if it is, so it is kind of understood that if it is far from 15 angstrom, the chances of tunneling is very low. Okay, so that's why like we think that if it is only possible if it is quite close. So we have actually some data where we have seen that when we are in the single entity measurements, we are actually seeing that the time of each peak under irradiation is slightly larger than that you observe under dark or with red. So that means that this electron, you see the peak, means at that time point, that time kind of tells you that charge transfer is happening. And if that is actually larger in case of your 532 nanometer compared to dark or red, that means charge transfer is happening for a larger time. Now, in each of the cases, the exact impact will happen for the same time. That doesn't depend on the light. So that means the charge transfer is actually happening slightly early, means it gets some more time. So even when it is not exactly in contact, maybe very close, still you start seeing the effect of this. So this exact 15 angstrom thing we are taking from literature, but this we have solid data to prove that at least even before it collides, it starts to transfer charges to the electrode, and that's how we come to it.
Okay, yeah. Okay, so is there any other question? If not, then let's thank Dr. Ganguly for very interesting presentation. So thank you very much. So let's move to our next presentation is Mr. Pilla Lamari Sri Krishnarka, and he's topic of presentation is towards, just a minute, towards breath, humidity sensing and opportunities. So regarding Mr. Sri Krishnarka, he is a PhD student of IIT Madras, and his current research activity on wearable sensor for healthcare. Over to Mr. Sri Krishnarka. Yes.
अरे यार हवा लगती है, जरूरी है बीमार हो जाओ तो फिर बस करो, डाल लो।
2 minutes more. Kindly wrap up. 2 minutes more. Thank you very much, Mr. Sri Krishnarka. So now the forum is open for discussion. If anybody has any question, please ask. So if not, I have one question that you said that you have used the sensing material is RGO and GEO. Mainly these two, or you have used other materials also? Okay. And you, there is a difference in the oral breathing and nasal breathing. You have shown that one. So why it is? What is the reason behind this? Okay, because of that. Okay. And you are showing that there is a durability of almost 60 minutes. It was happening. So yeah. Yeah, so this is that is the optimum you can go, or it depends on other factors also. Oh, okay. Okay, so anybody else has any question? So if not, then again, presentation. Thank you very much. Thank you. The next presentation is Mr. Orijit Jana. His topic is nanomolecules with atomic precision. Mr. Jana is a PhD student in IIT Madras, and his current research activity is on synthesis of metal nanocluster for potential applications. Over to Mr. Jana. Yes, Mr. Jana, please.
Am I audible, sir?
Sure.
And my screen is also visible, right?
Yeah, it's frozen.
Now it is fine.
I'm not sure if you can change the slide and see whether it is.
Just a minute.
Yeah.
Arijit, will I share?
So Mr. Jana, his screen is frozen. So
Arijit, will I share on behalf of you?
his screen is frozen. I think he's having
I think
some
network has an issue, I think.
Okay.
Arijit.
So it's still
Just let me share his screen. Maybe he can present.
okay. Yes, he is now online.
I'm sorry for the internet connection.
It's okay. Yeah, you are online now. Please go ahead, Mr. Jana.
Can you share the slide, please?
Yeah. You wait.
Okay, Dr. Saurav is sharing his presentation, and Mr. Jana will present accordingly.
Okay, good afternoon, everyone. So today I'm going to present the topic titled as Nanomolecule with Atomic Precision. So from the title of the topic, you understand that I am going to present some molecules which have some precise number of atoms. Go next. So this specific class of particle we called as nanoparticle or nanocluster. Go next.
Next slide, please. Shut up. Yes.
No, I think
Yes.
one back. One slide back. Yeah. So this kind of particles is holding the gap between single atom and traditional nanoparticle. And mostly these particles have the dimension of 1 to 3
Sorry,
nanometer.
just wait. I am sharing my screen, not your PPT. Just wait. Now it's okay. Oh, sorry. Switch one. Who is this? Snarka? You can. You have. Sure. Thanks.
Okay, now it is visible to me.
Yes.
Am I audible?
Yes. Yes. Please go ahead now.
Okay, so this specific class of particle, mostly you can see they have a metal core, and that metal core is protected by surface ligands. And organic molecules are mostly used for surface ligands like thiol, phosphine, carbene. And due to their quantum confinement, they have a discrete electronic energy level, and they have multiple absorption features, what you can see in their absorption spectrum. And mostly this class of particle made up with gold, silver, and copper. And now I will discuss on some of the silver and copper nanocluster. And the last decade, we observed rapid expansion of the field through various reports from different research groups in terms of publication as well as their molecular structure. So you can see the figure C, where there is a large number of structures are reported from various groups. Now, why this class of particles are so important? Because next, yeah, because if you can see this slide, so this slide is the crystal of one of the cluster, and you can see it is highly uniform and also a beautiful color. And this is the structure, whatever is resolved from this single crystal. So this is silver 21 nanocluster, which have 29 number of silver atom that is protected by this carbonate, this thiols ligand. And there are several other reports of different silver nanocluster. So in my work, we have synthesized some of the silver cluster. Go next. And if you see the whole family of this cluster, so they have different core cell structure, where the core is made up with metal atom and the cell is mostly ligand. And if you can dissect the core, so the inner core of the cluster is made up with this kind of octahedral, cube, or icosahedral. And then there is an expansion of the core like a core cell kind of geometry, like one metal core is protected by one cell, and that can be extended to even further. And there is an interface between this metal atom as well as ligand. And finally, they have the different type of ligand, like you can see the thiols in the top, and this is the alkyne ligands, and this is the different amine ligands. Go next. So this is one of the interesting silver cluster, which have a propeller shaped structure due to the arrangement of these carborane ligands. And if you can see the propeller in different orientation, you can see this propeller can be viewed as a double rotors of this carborane ligand. And this structure shows interesting photoresponsive behavior. If you illuminate the cluster with light, so there is a vibrational motion of this wing. And this cluster, go next. We have characterized through this visible absorption studies, where this cluster shows multiple absorption band. So that's all indicating their molecular nature. Like you can see the multiple absorption band like 307, 355, 396, as well as 491. And this is the color of the solution. And we have characterized this cluster through mass spectrometric studies, where the specific peak at 4893.43 is characterized with the cluster composition as silver 21, 12 of that carbon thiol ligand, and true triphenyl phosphate. Go next. Then we are going to discuss about some copper nanocluster. So that we call it as a copper 4 cluster, which have a tetranuclear copper 4 core, and that copper 4 core is protected by this carbon thiol ligand. And this is the three different molecule we have synthesized, and this is the crystal structure of these three cluster. So first one is we call it as a copper 4 orthocarbon thiol, and the middle one is metacarbon thiol, and the last one is iodinated carbon thiol. And the interesting thing of this cluster is that as we change the ligands, their inner core structure, that is this copper 4 S4 inner butterfly, so they are going to be flattened. And this flattening of the structure has their interesting effect on their photophysical properties. Go next. So there you can compare the photophysical properties of this cluster. So this first one and the second one is green emitting in their crystalline state, whereas the last one is orange emitting due to the flattening of their structure. Also, we have observed this emission is coming from the crystalline state. They are mostly non-emitting in solution, but when they are forming crystal, they are becoming brightly emitting. This behavior is called as crystallization-induced emission. Then we have studied their emission behavior in different stimuli responsive conditions, like we put mechanical pressure as well as thermal condition to check the tuning of their emission. And we observed that this first derivative is only mechanically responsive, but the last one is mechanically responsive. Go next. So this is the mechanochromic responsive behavior of this cluster, where you can see upon grinding this copper 4 orthocarbon derivative as well as metacarbon derivative converting from green to yellow, which is again coming back upon solvent fuming. So this behavior is called reversible luminescence interconversion, and this behavior we need to observe for the iodinated derivative due to their flattened structure. And we have checked their powder XRD behavior, and we have observed that they have an interesting phase transition from crystalline phase to amorphous phase. And in the amorphous phase, they are mostly yellow emitting, but when again they are becoming crystalline state upon solvent fuming, again they are becoming green emitting. Go next. Also, we have observed thermal dependency behavior. So where you can see upon heating this cluster from room temperature to 200 degrees centigrade, their green emission is converting to the yellow emission. And this is corresponding to their PL behavior, where the particular peak at 533 nanometer is shifted to 2 double peak at 511 and 612 nanometer. So this is indicating their thermoresponsive behavior. And we have checked the powder XRD pattern of this cluster, and we are infer that due to their lattice vibration, there is a molecular distortion, and due to their distorsive nature, there is this thermoresponsive behavior. Go next. Also, this kind of material can be used for X-ray radioluminescence application. If you can shine X-ray light by using for this material, you can see there is an interesting emission, and this behavior is called X-ray radioluminescence. And by using this behavior, you can coat some material, some screen, and you can use the material for this X-ray scintillating application, where you can see this kind of helical structure as well as this fiber can be made for this X-ray imaging application. Go Go next. Also, this kind of material can be used for different photoluminescence space application, where you can see they can be used for crystallization induced emission as well as thermal emission, as well as if you put more and more pressure to this material, they are becoming more and more emissive. So that is called pressure dependent emissive behavior. Also, this material can be used for some solvent trapping behavior, where this particular cluster trap different solvent like ethanol as well as cyclohexane, astronitrile, and their emission gradually shifted from green to yellow. So this behavior is called solvent-induced structural change. And there are some report of this cluster which can be used for this kind of behavior. Go next. Also, cluster can be used for interesting single particle conductor. So where you can see one single crystal of cluster can show the directional electricity. So the particular direction of C, they are mostly conducting, but in the other direction, like the A direction, they are non-conducting. Also, you can use this kind of device, which called as mechanically controlled break junction device, where you can measure the conductivity of one single cluster. So single cluster can go and sit in the two gold electrode, and there you can measure the conductivity of one single cluster. And from this study, people refer that as soon as the dimension of the particle is increasing from silver 25 to silver 374, there is more conductance from the particle. So this kind of selective particle can be used for selective single particle conductor. Go next. Also, this kind of cluster can be used. Yes, just a minute. Also, this kind of cluster can be used for some sensing application. So we have used this copper for ICPT cluster and do the electrosphere deposition of this cluster on a water surface, and we make some kind of thin film. So this thin film is some kind of porous structure, so that you can understand through their different optical and scanning electron microscopic studies. Then we have studied this film for nitrosensing application. Next. So where you can see this orange emitting flame become non-emitting upon this nitrogen exposure, and this exposure is reversible. So if you expose the nitrogen, then emission is quenching. If you heat the flame, emission is regenerating back. This kinetic is mostly exponential and nearly expand for desorption process. And if you do the flame for multiple cycles, like up to 5 cycles, we have observed its stability, and we have performed the IR studies to understand how this particular molecule is going and binding. And we are observing that there is some specific position where this particular molecule is going and binding with the cluster. Go next. So this is the 4 different positions where this molecule can bind. So observe that the periphery of the carbon that molecule is basically binding compared to the other position. And this is the of the cluster, where you can see there is a specific bonding between carbon and the ligand and the nitrogen molecule. So to the conclusion, we have discussed about different atomically precise metal nanoparticles and their structural as other characterization, photoluminescence and X-ray behavior also have discussed. We have discussed stimuli response luminescence single particle conductivity as well as conductivity of single crystal. We test structural CNC can be used in sensing application like we saw this nitrogen. There are some other sensors like you can sense RC use this kind of film. So coming to for the funding and support. Also, thank you.
Okay, thank you, Mr. Jana, for very interesting presentation. Now, this is open for discussion. If anybody has any question, please ask. So if there is no question, then I have one question. So you have mainly used silver and copper as the core metal, right? Hello?
Yes, sir.
He had network issue.
Yeah, sorry.
Yeah, I am there. Yes, sir.
So
We have
you
used
are
silver and yes.
Okay, okay. And there is one slide you have shown that there is a conversion from crystalline to amorphous to again crystalline.
Yes.
So how you are controlling this, or how it is happening?
No, as prepared samples are mostly crystalline. So when we are grinding, that crystalline sample is converting to the amorphous sample. Then again, when we are putting the solvent vapor to the amorphous sample, so they are crystallizing, and again they are forming some microcrystal. So it depends on the condition. Like if you
So mainly
grind,
thermal effect. It is mainly thermal effect then.
not only thermal effect, it is like grinding effect as well as their self crystallization effect. In
Okay,
presence
the
of
grinding
solvent.
actually there is some temperature is generated. So in any case, yeah. So and one more thing is that you have discussed about this single cluster. So how many number of, I see that is AG 374. So the maximum number of atom in that cluster is around 400. That is the maximum you are.
Yeah, for that particular study, the people have used different cluster, whatever is already reported, and they have studied up to 374.
Okay, so in any case, what is the maximum number of atoms possible in a single cluster? Around that, or?
For silver, it is mostly up to 400. For gold, you can go up to 600, whichever is structurally resolved. Like you can see the structure. But for silver, you can go up to 400. Like 374 is nearly the highest for silver nanocrystal. For copper, it is less. Copper, you can go up to 100.
Up to 100.
Because,
Okay.
yeah.
Okay.
The copper are not that much explored. Gold and silver are mostly explored.
Okay. 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 So yeah. Any other questions? So if not, then again, we thank Professor Mr. Jana for this nice presentation. Thank you very much.
Thank you.
So we are now having our penultimate presentation by Dr. Moyuk Ray. Dr. Moyuk Ray is from SN Bose National Center for Basic Sciences, Kolkata, and his topic is let me see. I'm sorry, I'm just. Your topic is the last one. Large anomalous new Nernst effect in ferromagnet Fe3Ge at room temperature. Over to Mr. Ray, Dr. Ray. I'm sorry.
Yeah, thank you to the organizer for giving me this opportunity to present my work here. And today I'm going to talk about that the observation of large anomalous Nernst effect in carbonyl lattice well ferrometallic system Fe3Ge. So let me just check this. Yeah, so I will be talking about this large room temperature anomalous Nernst effect observed in carbonyl lattice well ferrometallic system Fe3Ge. So my talk is little bit different than the earlier three presenter in this session. And this work actually done while I was working as a postdoctoral fellow at the University of Tokyo. So here are my collaborators, Dr. Taishi Sen and Akoti Sakai, and my supervisor, Professor Satoru Nakasu. So before going into the details of this, much of the details of the Nernst effect, I would just like to briefly introduce with this the theoretical description of the Nernst effect and what are the factors decide the magnitude of the Nernst effects in material, specifically in this magnetic materials. And I will discuss the recent days scenario in context of the Nernst effect. And I will discuss about that why I choose this material with carbonyl lattice. I will of course discuss its magnetic property and the electrical and thermoelectric transport in this system. And finally, I will show some scaling plot, and I will show you that how our compound is paired with the already existed ferromagnetic as well as the antiferromagnetic materials. And in the last slides, I will show you that the band structure calculation done by our theoretical collaborator, and I will conclude there. Yeah.
So if we go by the theory, so we know that the textbook definition of the Nernst effect actually. So it is nothing but the creating a electrical voltage while you are creating a temperature gradient in the orthogonal direction of the voltage. But in the physics, unless you measure any quantity, specifically its loses importance. So while measuring Nernst effect, you need to have sample with specific dimension. So in the preferred dimension is the rectangular one. So you need to polish your sample in the rectangular shape, and then you have to connect to a heater in the hot zone and as well as the cool zone, and you will connect the voltage along this direction. And you will have to use this formula to quantify this Nernst effect in material, which is nothing but this Lx is the distance between two temperature leads. So that means you have to take care of the distance from this hot zone to the cold zone. And the Ly is the distance between to the voltage wire. So that means the width of the sample. So why we look after this Nernst effect while already existing Seebeck effect was doing fairly at the room temperature? The problem was with this Seebeck effect that it's a two-terminal device. So you already means you creating the thermal gradient along this using the same terminal, and you also measure the voltage using the same terminal. So that means it has some issue with incorporating in this electronic devices. And also you do not have to need that both the N-type as well as the P-type thermoelectric material. So while just by using one kind of material, you can switch the voltage direction of the voltage in the using the Nernst effect. But is that all good in the case of Nernst effect? The answer is clearly no. The magnitude is not the large enough for the practical application. And also it needs to use the magnetic field. That is a major drawback. So the Nernst thermal power actually what we measure in the experimentally, as I shown here in this slide, so can be decomposed in two parts. One is the normal component, another one is the anomalous component. So the normal component is basically scaled with the magnetic field. So as you increase the magnetic field, the magnitude will increase. So it goes linearly with the magnetic field. The another part is called the magnetization. Anomalous part which is scaled with magnetization. So as the magnetization increases, this component actually, this part of this Nernst thermal power actually increases. But recently found that even there is no magnetization in sample, such as non-collinear Mn3Sn, where the magnetization is vanishingly small, but you can get a sizable Nernst effect, Nernst signal. So from there on, so people start to find out what are the things actually contributing when the magnetization still vanishes and we are getting the Nernst thermal power in the system. Then the theoretical model comes into play, and they find that this is coming from some intrinsic origin rather than the magnetization. Actually, it comes from the band structure of the materials itself. And if we just more generalized it, it comes from the net Berry curvature. So Berry curvature actually is nothing but the magnetic field in the momentum space. So even if you are not applying the magnetic field from the outside in real space, so it's the material itself is actually creating some magnetic fields inside it. So which actually gives you the Nernst thermal power. So the necessary condition for the large Berry curvature is to have some oil points near the Fermi energy, and a material with tridimensional symmetry breaking as well as the inversion symmetry breaking, you can have such kind of oil points near the Fermi energy. So in the case of thermoelectric device, actually, one of the major parameter we actually look upon, that's thermoelectric conductivity, which actually gives you the potential of a material as a thermoelectric devices. So that is actually related with the Hall conductivity, just the first derivative with the energy. And if you look upon it goes into the absolute zero, it's the Hall conductivity depends only on the Berry curvature and the Fermi-Dirac distribution function, while the thermoelectric conductivity depends upon this Berry curvature as well as the density of a state. So to increase the thermoelectric conductivity, you need the Berry curvature, large Berry curvature as well as the large density of states near the Fermi energy. So next, the material information. So this material actually grown using the chemical vapor transport system. So these are the image of as grown crystals. So this longitudinal direction is the C-axis, and the other direction you have to use the Laue method. So in this slide, actually, what I am going to tell you that why we choose this this kind of system with Kagome lattice. So recently the Kagome lattice comes into play that it's a corner sharing triangle. So if the material is antiferromagnetic, so these materials can never be ordered at even at the absolute zero, because one spin will be always frustrated. But ferromagnetic case, you can have a breathing Kagome lattice, and these breathing Kagome lattice recently can give you a higher order topological phases as well as the flat band near the Fermi energy. That actually gives you the large anomalous Nernst effect. These are the magnetization, so M versus T curve. So from there, we just found that the materials, the easy pin axis is along the C direction until the temperature of 360 Kelvin, 362 Kelvin. And below that, the spin become oriented along the AB plane. So here is the picture, actually, schematic diagram. So when you are applying the magnetic field along the C direction at high temperature, I mean that up to that 362 Kelvin, the spin is along the C direction, and below that the spin is lying on the AB plane. And here you can find that even at the high field, the magnetization is very feeble temperature dependence up to the 400 Kelvin. And this, while MH actually suggests you that the AG axis is along the AB plane, while the C axis is the hard axis at 2 Kelvin. So next slide, we will discuss about that the longitudinal resistivity as well as the Seebeck effect in this material. So from the longitudinal resistivity, you can see it's a just general metallic behavior when we applied field along the A axis as well as the C axis. And the Seebeck effect actually goes on continually decreasing with the temperature. So this is very common things for the metallic system. And if you look upon, just concentrate around this low temperature region and just plot it rho versus T square. And if we want to calculate this A coefficient, which comes is about 0.8 into 10 to the minus 3 micron per centimeter per Kelvin square, and we will actually going to show you that where, and from this heat capacity measurement, we also calculated this gamma. So we put this A coefficient we calculated from this resistivity as well as this the gamma coefficient we calculated from that heat capacity in this Kawasaki wood plot. This plot actually gives you this, tells you about that whether your system is a free electron system, that means whether your system has any electron correlation or not. And on the other hand, it will also suggest you whether if there is a correlation or not in the system. So from this plot, this point actually, for the Fe3G, in which you can find that it is actually very close to the strongly correlated electronic system. So that means if there is a correlation, we can expect some flat band near about this Fermi energy that actually gives you the large density of states around the Fermi energy, which in turn actually gives you the large thermoelectric conductivity. So we measure that room temperature because we are looking for the practical application. So we mostly focus around this room temperature region. So these are the measured thermal power as a function of magnetic field at 300 Kelvin. So it is quite large compared to the other ferromagnetic materials, which I am going to show you in the next few slides. And these are the Hall effect in the same temperature. And these are at the temperature dependence. I mean, this axis we have the temperature, and this axis we have the thermal power at a fixed field. And this is also the Hall conductivity as a function of temperature at a fixed field. So if we just convert this Hall resistivity into Hall conductivity, you will get that our Hall conductivity basically comes in the intrinsic region. So that means what are the contribution or what are the factor actually deciding this large Hall conductivity is coming from the intrinsic. It is not coming from this any magnetic or magnetic field related stuff. So we just one brief confirmation that there is some intrinsic contribution in this material, but there is no experimental evidence still yet to confirm this evidence. So if we just calculated this thermoelectric conductivity, what we have already measured in these slides, it's only. So there is two terms actually. One is contributed negatively. So this red one and this blue one is actually contributed positively. So if you just add up these two terms, you will get the temperature behavior of your Nernst thermoelectric conductivity. So it increases with the temperature, and room temperature is about 2.25 ampere per Kelvin meter. So when we plot this one, alpha versus T, and as well as the T in the similar plot, in the high temperature region, you can see that it is following a T log T behavior. That means, so there is a clear violation of mode relation beyond this 70 Kelvin, which is very hallmark signature of topological ferromagnets. So I was talking about that our materials has some well nodes and as well as the topological, but I have not proved any experimental signature. So there is an experimental actually signature. We can prove that the material hosts some kind of a well points near its Fermi energy that is called the evidence of chiral anomaly. That means while you are applying magnetic field as well as the current in the same direction, you will get the positive magnetoconductance. And while you will move upon this configuration, you will go the negative one. So in this configuration, this green one actually, so in this configuration, we applied magnetic field as well as the current in the same direction. You can see that it is a positive magnetic field. And as we move from this configuration, that means when the magnetic field is applied along the Z axis and current is along the X axis, we are going to have the negative magnetoconductance. So that is one experimental evidence actually tells you that the our materials system hosts some kind of a oil points near the Fermi energy. Sorry. Just 1 minute. Just 1 minute. Yeah. So when we plot this now thermal power versus magnetization, so that this plot actually gives you that how much magnetization you need or how much magnetization gives you how much thermal power. So this is the red line actually the limit of the ferromagnetic material. So any ferromagnetic material cannot go beyond this red line. So if we look upon our material, which is Fe3G actually, so it comes around this point. So this position actually well beyond the the limit of the up to which the magnetization can produce. So that means there is some extra contribution which is coming from this band structure of the material itself, and that is intrinsic origin. So we also plotted this thermoelectric conductivity of defined materials, and we found that our material is very close to the already existing material which shows the large thermoelectric conductivity. And these are the band structure calculation which actually support our experimental evidence of forming some well points near the Fermi energy. These are the points actually very close to the Fermi energy, which actually supports the our experimental evidence. And here we plotted this Hall conductivity as a function of energy, and also the thermoelectric conductivity as a function of energy. And this line we actually pointed out that where our Fermi well point actually placed in respect to the Fermi energy. It is about the 60 MeV from this Fermi energy. In conclusion, we would just like to tell you that we found that this is a single crystalline material which has easy access in plane along this x-axis below 360, and we also observed that now thermal power as well as the thermoelectric conductivity cannot simply explain by the scaling law of the magnetization. So some extra contribution which is coming from the band structure of this material itself, and the Kagome network of Fe atoms actually ferromagnetism, and also the correlation which is proved that some kind of flat band structure which favors the exotic oil state, and also some kind of a lithness kind of a transition can at finite temperature can also be expected in this system. And here I conclude, and thanks.
Okay, thank you very much, Dr. Ray, for very interesting presentation. So the forum is now open for discussion. Do you have any questions? You can ask.
Moyuk?
Yeah.
Other than the wild semi-metals, what other category of materials do you, consider for this kind of nuanced experiments, basically?
So, so as I discussed that, so the ferromagnetic materials has some limit actually. So in these slides, the rail line is the limit of the ferromagnetic materials. So even iron cannot go beyond this this rail line. So if you just look upon just using the magnetization, you cannot go beyond this one. So you need some
what is
extra
the
combination.
y-axis, Mayuk? What is the y-axis? I can't see properly.
So this axis is announced thermopower actually in microvolt.
Okay.
So you need to come out with some kind of materials by manipulating its crystal symmetry, also the band structure. And to increase or go beyond this rail line. So now this is the research to how far you can go beyond this rail line.
Okay, so your material lies in the very top, right? Like
yeah. So this one, yeah.
Okay.
Not very top. There are many other samples. So my one is this one, the Fe3G hexagonal. So there is other phase is Fe3G Ga. This is gallium, Fe3 gallium. So this pink one, which is at the top, and my system is around here. So this is hexagonal.
So the Kagome structure in hindsight gives a hexagonal kind of configuration only.
No, if you have the hexagonal crystal lattice, then there is a possibility you will have the Kagome lattice structure. So it is not that, yeah.
So it is the other way around, basically. If you have
no, not the other way around, yeah.
Okay, so any other questions? So if not, so let's again thank Dr. Ray for nice presentation. So thank you very much. So we are now, we have our last presentation by Dr. Madhumita Choudhury. She is a postdoctoral fellow of IIT Kharagpur, and her presentation will be suppression of spin deviating in ultra-thin polymer films by incorporation of nanoparticles. Welcome, Dr. Choudhury. The forum is yours.
Thank you so much for the introduction. So I'll share my entire screen. So, good evening, everyone. I am Madhumita Choudhury. I'm a postdoctoral fellow at the Instability and Soft Patterning Laboratory at IIT Kharagpur. Our group mainly focuses on soft matter systems such as liquid crystals, colloids, polymers, with special focus on soft patterning and lithography. So today I'm going to talk about suppression of spin deviating in ultra-thin polymer films by incorporation of nanoparticles. So polymer thin films and coatings are widely used in a variety of everyday applications because of their superior properties, such as polymer-based adhesives, they show high temperature resistance. Polymer-based paints, they show corrosion resistance and wear resistance. Then polymer hydrophobic coating of polymer is applied to make non-stick cookware. Polymer coatings are also being used to make coated textiles. So if you have accidentally dropped your tea or coffee on to this kind of coated textile, then instead of getting absorbed and spoiling the fabric, the liquid will simply roll off, leaving your fabric unspoiled. Then polymer coatings are also being used for making anti-reflective coatings for glare-free lenses. So because there are so many applications, so it's also important to know the fundamentals of polymer science, and that's what we do. So we create these polymer thin films in our laboratory. So spin coating is one of the very commonly used techniques to create such thin films in the laboratory. So basically what we do is a few drops or a very small volume of the polymer solution is dispensed onto a substrate, which is then rapidly rotated with the help of a spin coater. So around 95 to 98% of the solution is simply ejected out at the very outset and the remaining solution, it basically spreads out on the substrate under the effect of the radial effect of the centrifugal force. So there's constant evaporation from the remaining solution. And at the end of the spin coating process, after the entire solvent has evaporated, what you get is a thin solid film on your substrate. So the thermodynamic stability of such thin solid films, it's decided by the spreading coefficient, which is basically the energy per unit area difference between an uncoated substrate and a coated substrate. So it's expressed in terms of the surface tension of your solid substrate, the surface tension of your liquid, and the interfacial tension. So if the spreading coefficient is positive, that means your energy has decreased upon coating. What you have is a stable film. On the other hand, if your spreading coefficient is negative, that means energy has increased upon coating, and what you get is an unstable film. So even such thermodynamically unstable films coated on non-wettable substrates can be created or can be coated by this method of rapid rotation. So once the film has been coated, once the solvent has evaporated, what you have is a kinetically trapped film. So even if it is thermodynamically unstable, it won't rupture under ambient conditions. So such a kind of film, thermodynamically unstable film, can rupture only if the temperature of the polymer has been increased above the glass transition temperature. So above the glass transition temperature, basically the viscosity of the polymer film, it drops and it may rupture. So this rupture in thin films is governed by van der Waals interaction. So we know that the van der Waals energy between two molecules, it drops as d⁻⁻⁶, where d is a separation. But in the case of thin films, the excess free energy due to van der Waals interaction, it drops as d⁻². So it drops off more slowly. So this term, the excess free energy term, it remains effective to distances of around 100 nanometer, and at larger distances, it goes to 0. So in films which are around 100 nanometers or thinner than that, what you have is this kind of excess free energy due to van der Waals interaction. In very thick films, which are few hundred nanometers or even micron thick, you don't have this excess free energy. That's why if you have a thick film, and if there are capillary waves due to thermal fluctuations, then immediately these kind of thermal fluctuations or these surface capillary waves, they are damped out under the effect of the stabilizing influence of surface tension. Whereas in the case of a thin film, if you have surface waves generated due to thermal fluctuations, then such kind of thermal fluctuations can either increase or decrease the excess free energy. So if such fluctuations, they decrease the excess free energy, that means such fluctuations are favored, then those fluctuations will grow, and ultimately it can lead to the rupture of the film. So this is expressed by a positive disjoining pressure. So that means such ultra-thin films, which are less than 100 nanometers, coated on non-wettable surfaces, they can rupture if the disjoining pressure is positive and large enough to overcome the stabilizing influence of surface tension. So if you have this kind of thin films, which are less than 100 nanometers, if you anneal the films above the polymer glass transition temperature, then basically these films can rupture. So you can see you have an initial uniform film, and then you find that there are few holes in the film. So with time, these holes, they grow, and finally the holes, they merge together. And finally what you have, that the entire film has ruptured. Now you have a network of polymer fibrils, which ultimately decays to polymer droplets. So your entire film has ruptured. So this kind of rupture is, of course, is undesirable from the point of view of coatings. Now, spin dewetting is a slightly different phenomena where dewetting occurs during spin coating itself. So like I said, that during spin coating, we drop a few drops of the polymer solution onto a substrate, which is then rapidly rotated. There is most of the solution is ejected out of the substrate, and whatever solution is retained on the substrate, there's constant evaporation of the solvent from that solution. And as the solvent evaporates, basically the concentration of the solution, it gradually increases. So at one point of time, the concentration reaches a saturation point, and when the saturation concentration is reached, film deposition starts. So film deposition starts when this saturation concentration is reached and not before that. So at the end of the process, of course, when the entire solvent has evaporated, what you have is a uniform thin film left on the substrate. Now, suppose I keep the rotational speed fixed, then I can expect that on decreasing the polymer concentration, I should get films of lower and lower thickness. That's what also happens. For example, in case of polystyrene films, when I coat the films at 2500 RPM in 60 seconds, at 1% polymer concentration, I get a film which is around 50 nanometers thick. At 0.5% polymer concentration, I get a film which is around 25 nanometers thick, and so on. But the question is, can this graph be extrapolated to lower and lower polymer concentrations? That means as I keep on decreasing the polymer concentration, should I keep on getting a film which is thinner and thinner indefinitely? So the answer is no, because below a certain critical polymer concentration, we stop getting uniform films. So what happens is, now there is constant evaporation of solvent from the solution which is present on the substrate. So if the solute concentration or the polymer concentration is too low, that means your solution is too dilute, then the solution, it basically ruptures under the effect of van der Waals interaction within the solution layer before the saturation concentration is reached. Now, like I said, that the saturation concentration is the concentration at which film deposition starts. So since the solution layer itself ruptures before the saturation concentration is reached, so what happens is that instead of getting a uniform film, you get the solute is deposited in the form of droplets or patches. So this is what spin devetting is. So if I start with initial higher polymer concentration, these are all atomic force microscopy images, and I keep on lowering. So here the polymer that is used is polystyrene. So I keep on lowering the polymer concentration in the casting solution. So I begin with a solution which has 0.05% weight by volume of polymer. As I keep on lowering the polymer concentration, you can see that from in the beginning, at higher polymer concentration, we get a uniform homogeneous film. At a lower polymer concentration, instead of a uniform film, now you have some holes in the film. At even lower polymer concentration, what we get is this kind of a network, a polymer network. So you can see that the darker contrast is basically the substrate, and you have these this polymer network on the substrate. So this is the critical polymer concentration below which we start getting spin devetted films. So instead of a uniform film, what we get are these kind of droplets. So as we keep on lowering the polymer concentration further and further, we get these spin devetted droplets, which are of lower and lower height and smaller diameter. So one question that comes to mind, of course, this kind of devetting, like I said, polymer devetting can be undesirable in certain cases of coatings, etc. So the question is, can this kind of spin devetting be suppressed? So it's already known that thermal devetting in thin polymer films, like when the film is annealed above the glass transition temperature of the polymer, so such kind of thermal devetting in thin polymer films can be arrested by adding a small amount of nanoparticles to the casting solution prior to spin coating. So this was already established in the pioneering work by Kathleen Barnes and Alamgir Karim in the year 2000. They showed that if you add a small amount of nanoparticles to the casting polymer solution before spin coating and then coat the film, then basically what you get is a film which is stable against devetting. That means even if you anneal the film above the glass transition temperature of the polymer, the film does not devet, it remains stable. So it's known that the particles, they basically migrate to the film substrate interface, and suppression of devetting occurs by various mechanisms, such as the particles, they pin the contact line of growing holes. The particles, they also modify the substrate and promote wetting. And the particles, they also increase the local viscosity of the film. So taking cue from this, we also wanted to find out if these kind of nanoparticles can also suppress spin devetting in our films. And we found that they can indeed do so. So if I have an initial film, which is a spin devetted film, now if I add a small amount of nanoparticles, so here, for instance, I've added 5% nanoparticles. That means the weight of the nanoparticles is 5% of the polymer in the solution. So on adding a small amount of nanoparticles before spin coating and then coating the film, you get a film which has higher coverage. So here spin deviating has been partially suppressed. On adding slightly higher concentration of nanoparticles, we see that we can transition towards a film which has more and more coverage. So finally, at 15% of nanoparticles, we finally get a film which is fully stable, where deviating has been arrested by the addition of nanoparticles. So we have also tested the effect of nanoparticles on spin deviating suppression at different rotational speeds. So for instance, these films have been coated at 1000 RPM. These films have been coated at 2500 RPM, and you have the highest RPM at 4000. So you can see that as you go towards very high rotational speeds, the coverage of the film is lesser and lesser. So that is expected because at higher rotational speeds, splashing is maximum. That means most part of the solvent, the solution is basically ejected out. And the solution which is retained on the substrate is actually very less. So you get a morphology where the coverage is very low and you get these kind of droplets, spin deviated droplets. But even in these cases where the coverage was such low, where droplet kind of morphology was obtained, even these kind of morphologies could be stabilized by adding nanoparticles. You can see that as you increase the concentration of nanoparticles, you can see that you slowly, gradually increase the coverage of the polymer films, and finally at 30% particle concentration, which is a bit higher, what we get is a film which is completely uniform, where deviating has been suppressed completely. So with this, I would like to conclude. This is an ongoing work, so we are trying to stabilize different homopolymers as well as polymer blends, which are mixtures of polymers. So we are trying to suppress spin deviating by introducing nanoparticles in such films. So ultra-thin polymer films, they may spin deviate during the stage of film formation due to rupture of the solution layer. And nanoparticles can arrest this process of spin deviating. And of course, the mechanisms may be the same mechanisms. They may pin the contact line of growing holes and modify the substrate wettability, as well as they may also increase the density of the solution layer so that the saturation concentration is attained before the solution layer ruptures. So this results in deposition of uniform and continuous films. So with this, I would like to acknowledge my mentor, Professor Alberto Mukherjee, and all the other members of the Instability and Soft Patterning Laboratory at IIT Kharagpur. Thank you for your attention.
Thank you very much, Dr. Chaudhary, for a very interesting presentation. So now the forum is open. If you have any question, you can ask the question. Yes, Abhishek.
Yes, Madhumita, one question is about this form of this, when the droplets are formed, they seem to be in some hexagonal, arrangement. If you look at that, when at some level you see the like a droplet formation, right? I mean,
yeah, at high rotational speeds, right?
At high rotational speeds, yeah, exactly. So, any idea why that forms so?
Hexagonal arrangement, yeah, we have not really looked into it. Actually, I've like now that you have said, maybe we would look
I just
into,
I thought that it looked like a very nice patterning.
Yeah. Actually, these kind of deviating structures are actually being used to create these kind of nano and mesoscopic, structures as a convenient as a convenient route in soft lithography. So actually, that is basically interesting.
Yeah, maybe it is because the triangular lattice in 2 dimension is probably the stable one. That's probably the reason why it's thermodynamically it's.
Yeah, that could be.
Just.
Yeah, sure. We'll look into this.
That's
a new observation. Yeah.
Okay, thank you.
Okay, Subhranshu, any questions? Subhranshu is also asking.
Yes. I have no question regarding this topic, but I have one request to you. That industry has faced a lot of problem on aluminium material. Aluminium worn out is very high, where RPM of aluminium spheres is near about 3,000, 4,000 RPM. That's the life of the aluminum pulley or aluminum any spares is going down below 6 months or 4 months, 3 months. To tackle this situation, we generally we use higher grade aluminum. That price 3 to 4 times than existing market available aluminum. If you find out the solution, the coating through the coating technology, that's life of the aluminum should go up and 2 to 3 times from existing now. It will be helpful for industry.
Yeah.
Maximum industry face this problem. Maximum in India, industry face this problem.
Okay. Sure. Yeah. Shubhranshu, we'll look into this. Maybe, we can discuss later because we are working on polymer films right now. So definitely it will be nice to look into some other systems where, like you said, metals and all. If we can stabilize them. Yeah, sure. Surely.
Okay. Thank you.
Any other question? So I have one question. So what kind of substrate you are using? Yeah.
Okay, so these are silicon substrates which have been treated to make them hydrophilic, so as to allow the solution to spread on it, because hydrophilic substrate has high surface energy.
Okay, so you said that it's when the thickness is less than 100 nanometer, so below or above glass transition temperature, it is rupturing. So it is not dependent on any substrate. So for all substrate, this is the limit of the.
No, it depends upon substrate. Of course, it will entirely, like I said, the spreading coefficient is dependent upon your surface tension of the substrate, the liquid, like the polymer solution or whatever solution you're spreading, as well as the interfacial tension. So a combination of all the three will decide your spreading coefficient. So if the spreading coefficient is like positive, that means the film is spreading, the energy is decreasing upon coating, and if it is negative, that means it's basically a non-wettable substrate for that film. So only on non-wettable substrates, the film will de-wet, like PMMA. PMMA is stable on hydrophilic substrate. So even if you anneal the film above its glass transition temperature, it won't rupture because it forms a nice hydrophilic bonds with the substrates. So in that case, it won't rupture. On the other hand, polystyrene, it ruptures on increasing the temperature above the glass transition temperature. So then it depends upon the entire system, like whatever you're coating as well as the substrate, the entire system, yes. So it depends upon how favorably the film is coated.
Yeah. And a nanoparticle you're using is basically carbon nanoparticle, right?
Sorry, I forgot to mention it. Okay, so we are using, in this work, we have used gold nanoparticles, thiol capped gold nanoparticles. But we have also checked this with fullerenes as well. So with fullerenes also this actually works. So we have checked using both these nanoparticles. Yes. So.
Okay.
Fullerenes
and I understand. Sure. Okay.
Thank you.
Any other question? So if not, then we again thank Dr. Chaudhary for very interesting talk. And this is the way we just end this session. But before ending this session, we just discussed that there are very interesting topics covered in this session. One is by Dr. Ganguly, which is presenting the nano impact single entry measurement enables plasmon enhanced electrocatalysis, where he showed that different nanoparticles with coating with graphite, other things, there is plasmon resonance absorption and there is a movement of Fermi level. So very interesting applications are there. The second one is by Dr. Srikrishnarka, which is based on the paper-based sensors he used for breath analysis, which is very, very important. It's also in my field also, kind of. So very important for personal, interesting one. Then we are having the presentation by Mr. Orijit Jana by different nanomolecules with atomic precision. So he created different nanomolecules using different metal cores, and it has various applications in optoelectronics, photoluminescence, as well as sensors. fourth one is by Dr. Mayuk Ray. Is based on Kagome lattice of magnetoresistance. Kagome lattice. Yes, for ferromagnetic abnormal Nernst effect in ferromagnetic material. It's a very interesting topic. And then the final one is Dr. Madhumita Chaudhary, who is presented the duetting effect through polymer coating on various substrate, and then it continuity you include with incorporation with various metal nanoparticles. So these are having very interesting applications. So this brings the end of this session. I again thank all participants and all presenters and everybody here for participating in this session. It's very interesting one, very fulfilling. And also I again thank the SRF and SD team for organizing this session. Thank you very much. So let's end this session here. And before that, let's have some photo session once more. So I'll request Saurabh to have the photo session, and please turn on your
When there is
camera.
a photo session, I am always there.
Yes.
Please turn on your webcam.
And hi, Abhishek. It's been a long time. We haven't met. We are actually classmates in our masters. Yeah.
Just wait.
Abhishek, mute. Abhishek is mute.
Okay. Sorry, I just thought that I was talking to you, but I didn't. It's been a long time.
Yeah, 25 years, I think.
Yeah, it's crazy.
Yeah.
After really nice to see you.
Nice to see you too. Yeah. Yeah, Subhrangshu was the main person actually. We connect us.
Yeah, Subhrangshu has been the he's holding us together, I guess.
Yeah, right. And excellent initiative.
Yeah, very good. Yeah, exactly, sir.
We must give a big hand to him. Yeah.
Oh, absolutely. Yeah.
Your presence is very important.
He's always been extremely passionate. That
Yes.
I know because I have know him for such a long time. I know him from my childhood days. So
16, 14 years
yeah.
old.
So, yeah. So even more than Argo.
Right. Yeah.
Is the photo session done, or can we
Saurabh has already left. I think.
then it's done. I guess we there is no need
No.
to
He joined.
pose anymore.
No.
We don't need to pose anymore, I guess.
Saurabh, is it done?
Saurabh single-handedly, basically, conference is all done by Saurabh single-handedly.
Yeah. Okay. Very good.
I know.
Done.
Done? You're mute. Saurabh, you're mute.
You're muted.
Yeah. It's done. Thank
Okay.
you.
Okay.
Good. So we can.
Yeah, the event is not ended. Tomorrow
Okay,
we have a session. There is a huge long session for poster presentation. So I welcome you all and be there. There will be a nice session and followed by a also that scientific sessions is there in the afternoon. So please join at 11 a.m. Indian Standard Time. Thank you.
Sure. Yeah.
Okay. In that note, let's finish this session.
Yeah.
I once again thank you, everybody. Thanks everybody for joining
Thank you.
this session.
Thank
you very much.
you.
Bye.
Bye.
Bye.